Right now, this is our GitHub repo for this training. It's public. You can reach that over there, and then I also copy paste everything in the chat channel right now. So let's start with introducing John Snow Labs and Spark NLP, and then I will cover some NLP basics, and I will show some Spark NLP pre-trained pipelines, which is the backbone of our Spark NLP, which is very convenient for the starters. And then text pre-processing with Spark NLP, the intro part of any NLP task, and then I will talk about Spark NLP pre-trained models, which means that the first session will be a little bit longer. Let me mute you all in case I didn't. Okay, so I think I mute all. So John Snow Labs is a award-winning healthcare analytics company, which is the main developer and the supporter of Spark NLP library. We have been getting some awards in data ops and data science and healthcare analytics for the last few years. We started our business in 2017. So we got a lot of attraction, and then so many companies started to use our tools, which I will cover in the next slides. So why did we decide to develop Spark NLP? As you all know, I'm assuming that some of you already know what NLP is, natural language processing. There are already many different NLP libraries in Python. By the way, during this training, I will write all the codes in Python, but we cover 4 different languages: R, Java, Scala, and Python. So on the left-hand side, you see the other NLP libraries, which is mostly known by the other people. But there is no one single unified solution for all of your NLP needs. What is your NLP needs? What are these NLP needs? I will cover in the next slides, but we try to cover every aspect, every bits of NLP. And then we also, on top of that, we also try to cover the latest and greatest state-of-the-art algorithms and models in NLP research. So we have an active development team, like we release every 2 weeks. Just in 2019, we have released 30 version, and then in 2008 it was 26. So yeah, right now we are trying to deliver a mission-critical enterprise-grade NLP library and used by multiple Fortune 500 companies. And this is the only library that is fully supported by Spark, which means that you can scale industrial level NLP process. So, and trusted by many famous companies in the industry right now, naming a few like Microsoft, Google, Amazon, Intel. So these are the companies that we verified that they are using Spark NLP at the moment. And what are these NLP tasks? If you start with the basics, on the left-hand side, you will see that name column. These are the basics. These are the basic NLP tasks that you can see, like sentence detection, tokenization, stemming. So I will cover all of them one by one, what they mean. If you have no idea about them, don't worry. But I just want you to focus more on the Spark NLP column. You see that we cover all these tasks. So there is no other single library that would cover all the tasks at the same time, which is very striking at the moment. So according to some survey in February 2019, Spark NLP is selected the most widely used NLP libraries. As you see, this is the first NLP library in this list. So we can safely say that we are the most widely used libraries in industry, let alone healthcare models. I will cover that tomorrow, but I think there's no other big competition over there. Right now, we officially support the following runtimes. As I said, like 4 different languages: Java, Python, Scala, and R. And then we can deploy our models, and then you can run your codes in Databricks, Cloudera, Azure, AWS, and then run Intel processors. So, which means that we cover all the well-known runtimes at the moment. So Spark NLP is built on the shoulders of Spark ML, which is the machine learning library of Spark itself. You know that since its inception in Berkeley, Spark ML, Spark itself has gained a lot of attention in big data analytics industry, and right now it's still very widely used by several companies and institutions. Therefore, this is the only NLP library, and we cover, like, we are using the Spark ML pipelines inside our pipelines, and we can use our own models in Spark ML pipelines, which means that there is a fully compatible pipelines that we can use with Spark itself, because this is written with Scala, the same language of Spark. So we are totally compatible. So we will, during this training, you will see that we will be able to use many Spark commands in Spark NLP. So let's start with introducing the basic concepts in Spark NLP. So when we have a text, like a table of text, like a CSV file, or a large TXT file, like thousands of TXT files in a folder, and we want to apply some certain NLP task, like extracting named entities, or finding dates, or finding the clinical entities out of those texts. What we do is, well, we try to apply the NLP algorithm, NLP methods from the selected libraries like NLTK Spice. In Spark NLP, we use like the pipeline and the pipeline of annotators. Each annotators has different tasks in Spark NLP. Like one of them, like for example, we take the data frame here at first. Assume that we have a text column of a large CSV file. We take that data frame, and then we create, we feed into the Spark NLP. This is the entry point, which we call it document assembler, which means that right now we have that document, we can manipulate that document inside Spark NLP. And on top of that, we start putting different annotators according to our use cases, which is like a Lego. So we put like a stacking blocks, we put each annotator one by one in a pipeline. As you can see here, we start with document assembler, and then we start to do, like, we want to split the sentences at first, so we put this one, and then we want to tokenize, which means we want to get each words one by one, and then we want to clean the words, and then we want to get the word embeddings from each token, and then build a pipeline, so that whenever I feed my data frame with this single line, it will run all the pipeline, which is very similar what we do in sklearn in Python. So which means that we use this methodology, and every time we use another annotator, there is a new column created and appended to that data frame, which means that they are all accessible later on. So let's start with the basics of natural language processing, because Spark NLP is an NLP library itself. So which means that we need to know, we need to make sure that you all know what we are talking about in the basics of NLP. So let's start with lemmatization and stemming. These are the basic two tasks, like the most basic two tasks of Spark and natural language processing. The goal of both stemming and lemmatization is to reduce to inflectional forms of, and sometimes derivationally related forms of a word, so that you get the base of each word and then remove the noise, so that you normalize, standardize your inputs, and then which means that it will be easy to build a model with clean form of your text. So lemmatization is just use a lookup table to get a base form, like the MR is R, the base is B, liver is liver, lives is the base of is live. So we use a lookup table, which is already embedded in Spark NLP, which means that when we build the sentences and then lemmatize, we get the base words of each token. For the stemming, stemming is like dropping the common suffixes, like studies drops studies. So which means that we get the stem of each word. So it may not be a fully understandable token, but it's still useful. So you will decide which one to use. Both used interchangeably, so it will depend on your use case. So which means that when you use the stemming, you drop the suffixes, and then you end up with a base form of each word, but may not be in the dictionary. Stop words removal. Stop words in most of the NLP tasks, like for the classification purposes, for example, stop words are removed or excluded from the given task so that the more focus can be given to those words which define the meaning of the text. As you can see, it was a bright cold day, so it was this tree token is useless in terms of the meaning of this text. So bright cold day are most useful, like to define the true meaning of the task. So in order to help the model to generalize better and find a pattern inside our data, we usually, for any NLP, most of the times we try to remove those stop words. In English, we have like around 500 different stop words, but you can come up with your own stop words in clinical stop words, financial stop words, etc. And then, for example, if we apply stop words removal and then stemming, that's what we get, which means that it's very, so any other sentence using different stop words will be still be the same on the right hand side. So spell checking and correction. This is the only NLP library that has spell checking embedded itself right now. And we, on top of that, we use 3 different approach for spell checking. For example, Harry Potter is a great movie. As you see, like this is, there is a typo here. When we run our pipeline, when we run our spell checker, we get the correct version of each word. So which is very cool when you try to remove the typos or normalize your data. Because if in one text there is a movie and the other text there is another word which means movie as well, so you want them to be same to build some classifier later on, which means that spell checking is very important in NLP tests. Normalization, like the cleaning the task, if you want to have just the alphabetical letters or remove all the digits or remove some charts that is not relevant, like an ugly charts, that is like when you parse some data from web and then you end up with some ugly characters in the middle, so you want to get rid of them. What we do is we have a normalization annotator, so when you apply that, you end up with this clean form. We also have, in the same normalization, we have the slang normalizer, which means that in the social media, especially when you get a data, you will get so much abbreviations, slangs, like some sort of weird abbreviations. So we have a slang normalizer, which uses basically a lookup table, and then you get an understandable text at the end. Part of speech. Part of speech is the special label assigned to each token, like a verb, noun, adjective, determinator, etc. So which means that each word has different part of speech tag according to its position and role inside a sentence. And these are all important features when you try to build some classifier later on, or when you find some relationship between the tokens, like who is selling, she sells, etc. So which means that part of speech is very important for text classification and dependence parsing as well. Let's talk about dependence parsing. Dependence parsing is like we just talked about the part of speech. So if you want to build some dependency, we need to know, like we need to link the date entities to clinical entities, for example, or we want to know who did that action. So which we call dependence parsing. So it's especially important for extracting relationship between the tokens. So it's one of the pillars of NLP at the moment. And NER. This is the last slides before we start coding. So NER is the subtask of information extraction that try to locate and classify named entities. Like, what are named entities? You define that. But in industry, in NLP domain, we have several benchmark data sets and several deployed NER models. Like most of them are extracting people, companies, places, money. For example, Google is starting from branch, so Google is an organization, so it's detected by NER as an org. So if you want to extract, for example, all the people name from a given text, you can use this NER. Or if you want to extract all the cardiac arrest entities or all the cancer entities, you can train an NER, and then you run thousands of your text files, and then you extract, you can detect all your clinical entities, lab results, blood count, etc. it all depends on your use case, and it's very useful to filtering your data and build another model, because NER can also be used as a feature for like how many brain entities, how many liver entities are there in your text, and then you can use that as a feature for your text classification purposes. So let's start with first and second notebook. So I will ask you to go to that chat menu, and then you will see notebook 1 and notebook 2. Just click on the first one. When you click on the first one, you will end up with this one.
Sorry to interrupt, but we do not have the repository of the presentation or the Git repository that you're showing.
No. Did you check the chat? Please see the chat menu of MS Teams.
Yeah, but we don't see anything in there. Oh, we don't see it. Probably that's because you have pasted it before we joining.
Okay, let me paste again. Now you get it, right?
Yeah, looks like, yeah.
Okay, you will just click on the first one. The PDF is the slides. You will just go to the first and then start with collab.research. Okay. It's the first notebook. So you should be seeing this window. So please let me know if any of you failed to end up with this page. We are all good? Okay. You can try to replicate the same, and you at first need to start your session on the right-hand side. You will see connected to hosted runtime. You should click on that. This is like a remote instance, remote server that's served by Google for free for 12 hours. It has even GPU inside, which is and TPU, which is very convenient if you want to train large models. So you need to see all this RAM and disk. So you need to be connected at first. If you are all connected, we can start coding right now. So in order to install Spark NLP into this instance, because this is a remote server, which is basically built for data science purposes by Google, but it has no PySpark or Spark NLP. So we can just install it. So this will be standard cell for every Colab notebook. So you don't need to check in detail. You will just run this one. Let's just run this one. Okay. So when you run this, it will at first, the first requirement for Spark NLP is JDK 8 and then PySpark. By the way, you guys are all using Databricks, so you don't need to do this on your Databricks, which is you will just import and start using. So you don't need to do that. We are doing this just for collab purposes. So if you want to share this notebook with your friend, they can all reproduce the same, because they will be using the same environment as you have been doing. So which is very useful tool for data science. It is right now. Everyone also shares collab version of their notebooks in GitHub. So it's running. So when you go to GitHub, you will see this one, workshop tutorial certification trainings. You will see all the notebooks here. When you click on any of them, for example, I click the first, you will see this notebook. This is on your browser. This is static. So when you click on open in Colab, you will have this one. To be fast, I just shared the link, like a direct Colab link with you, instead of going to GitHub and then click on that one. Okay, right now we have the Spark NLP installed. Now we can start importing and starting our session. When we do Spark NLP start, I think in Databricks you don't even need to do that. Spark session is already created, I think. That's what I'm told. So which means that you will just have that Spark session already over there. when we call start, it will load all the jars and the dependencies, libraries over there. Right now we are using the latest version, 2.4.5, as a Spark version, because we are sitting on the shoulder of Spark. It's 2.4.4 at the moment. So let's start with the basics of Spark NLP. So I will just start with pre-trained pipelines. Pre-trained pipelines is the already built pipelines for specific purposes. You can get the full list from that link, Spark NLP modules on GitHub repo. For example, for explain document, we stack some annotators one by one. You see here for the explain document. We already have document assembler, sentence detector, tokenizer, lemonizer, etc., and end up with spell checker. So which means that when we just use explain document ML and then fit on and then get a prediction for our text, we don't need to deal with what's going on under the hood. We will just, how do we do that? We just import this one. Like let's import Spark NLP.pretrained, import pretrained pipeline. And let's load explain document ML. So the name, this is the name that I get from this table. So if I want to use any of this, I check this name column and then language column, and I just use the same here. So which means that I'm going to download this explain document ML, and then it will be that the pipeline will be fitted on my local without doing any extra work. So and then I will just have a text, like a simple text, and then I will just get all these tokenized, like tokens, lemmas, stamps, and spell checkings. So right now it's 10 megabyte. It's just downloaded from S3, which is public, which means that anyone can use this pipeline. There are also clinical pipelines that we will discuss tomorrow. So assume that this is our text, and we want to process this text with this pipeline. So what we do is we just call, like, since pipeline is already loaded and assigned here, we will just pipeline. Let's define test doc. Okay, this is like runtime for each cell. You can just use this magic commands so that you can see the roll time or CPU time of each of your lines or cells to do some optimization later on. So when you do annotate, we just use annotate. This is the method that we use to get predictions from our text. So pipeline.annotate, and we use our strings here. Let's run this, which means that in less than 1 second, my text is fed into the pipeline and splitted, like sentence splitted. Tokens are extracted, lemmas, stamps, and part of speech are extracted as well. And also the typos are fixed in less than 1 second. So it returns a dictionary, like a JSON in Python. It has these keys: document, spell, like a document column, spell column. Document is exactly the same as the text that you put. Spell is the corrected version of your tokens, part of speech text, lemmas, token itself, stamps, and sentences. So let's see how many sentences we have. As you see from our text, there were 2 sentences actually. How is that done? As you see, even though I like this is like to be able to use the multiple lines in Python, so it's splitted by some sort of rule we call it, which we call it pragmatic rules. Not just taking into account the dots, we also use so many other rules to split the sentences, and we also have special splitter for clinical text as well. So we have 2 sentences right now. If you want to see the tokens, which means that we will get all the tokens from this document, so all the sentences. So you see that French other who helps, so we get even the punctuations are tokens, you know. So as you see, we get a list which can be used in any Python environment later on if you want to get the tokens and do some other stuff. So let's write like the part of speech of each token. Since they are both lists, in Python we can just zip and get the list, which means that like a write in a for loop, we can just zip them get a tuple, like a list of tuples for token and part of speech. Please do not, please try to intervene or stop me if I'm going fast or slow, so that I would know if I'm doing okay or not. So we have the tokens and part of speech for each token, because they are all identical, which means that there are the same number of part of speech for tokens, because they are identical, because we get part of speech for each token. And then if you want to also use stamps and spell, we can also do the same, which means that we can convert this to pandas data frame. So since this is a dictionary, we can just get all of them. This is a list. This is a list. This. Okay, this is a list of tokens, and then so which can just use as a dictionary and then convert it to pandas data frame. So when you run that, you will get a token column, corrected column, spell check column. Let's see how the correction works. You see this row? In original, it's Pioneer. We had a typo here. It's fixed here. You see, like the corrected version, it's fixed. And the lemmas and the stamps are also using the corrected version, because we use lemmas and stamps after spell correction, which means that we fixed that token and then we ended up with a corrected column. This is all done by pipeline itself. We are not doing this. You just run this, just pipeline.annotate, and then you end up with all this. So that was the pipeline that we call it explain document machine learning. So let's talk about explain document deep learning. The only difference is that from ML part of explain document is that we also have NER, which is trained on CoNNL 2003 dataset and using the glove word embeddings. So which means that you can get people, location, organization labels from your text by just using explain document DL. So we do the same here. We just call it, so it will download 168 megabyte to your local. By the way, let's see where are these models are downloaded. Assume that this is your local. On my left hand side, I see the disk of Colab instance. So on your home folder, the home folder in Colab is root folder. So there is a cache pre-trained folder that is created by Spark NLP, which means that this is your home folder, like your username on your local. And then you will have a cache pre-trained folder, which means this is already downloaded here. So you can use that without downloading internet. You can use in totally air gap network, so without internet. So you can just load from disk as well, like pipeline pre-trained pipeline.load. So since we already download two, it's already there. So even if you use this one, Spark NLP will check S3 if this pipeline is updated in S3 in AWS. If it's updated, the updated version will be downloaded again. If it's not, it will be used like the disk version, so which is very fast, and so you don't need to download again. So since it's downloaded and loaded and assigned to pipeline DL, let's annotate our test document again. It's again less than 1 second. We also get NER, which means name identity recognition. Let's see, like we have two entities from that text, French and Werner. Let's see in detail all the labels. I did all the steps that I just explained, so I'm just skipping and then showing you the pandas data frame version. So we have the tokens again. We have the NER labels, which means that name identity recognition labels for each token. Like this is the beeper, which means that the first token of any name. If there will be a surname or some other name like John Doe, it will be like beeper, iper. So which means that we can just concat later on, which is already done by pre-trained pipelines, by the way. Let me show you. Let's do spell checking. Here you also see the spell correction, right? If you don't want to deal with all the lemmas and stamps and NER, you can just use check spelling pre-trained model. You can just check the Spark NLP models GitHub page and then get the name, and then you can just use that, which means that you will just get the tokens and fixed tokens from your text. So let's do that. Okay.
Quick question. What's the position? How is that you're assigning the position column, and what's the significance? I mean, what's VBN and what is that?
What's
the POS, the position?
Okay, it's a part of speech. Part of speech,
okay.
like I explained, like a word.
Okay.
So there's a trained model in the pipeline. I will explain the trained model later on. This is all pre-trained pipeline, so you don't need to know where it gets this one. But we train our models, which means that it knows it's a trained model. We use perceptron approach for that on some public data sets, and it's trained on public data sets, and then try to get the part of speech of each word according to its position and relations.
Okay, thank you.
Okay, perfect. And NER is also a trained model. As I told you, it's trained with CoNNL 2003 plus GLOW 100 dimension dataset. Word embedding, sorry. So if you want to use check spelling, like this is check spelling, we can just download it. It's downloaded. As you see, it's also in the cache trained. And let's annotate, which means you can just get the token and check versions of everything, you see. So you don't need to deal with all the other columns at this time if you just want to apply spell checking on your large text. I'm showing you how to do that with simple text because this is a warm-up intro. But in the next hour, I'm going to show you how to use data frame, like how to transform and fit. So if you have a list of text, you have 1,000 sentences, or you have text files that you put inside a Python list, for example, and you want to use these pre-trained pipelines. So you don't need to have a data frame. Or you have a one data frame column in Python, pandas column. You just get the list, like convert it to list, and then you can just use this pre-trained pipeline on this text, which means that you don't need to run the pipeline one by one for each sentence, because this is a list of sentences, you see, like this is the first sentence, ending, and the second sentence, and the third sentence in the list. Let's run this, and now I can run the pipeline on this list, which means that I don't need to send each sentence one by one. What was the pipeline, by the way? Pipeline was the last downloaded version of pipeline was ML version, as you see. This is the first pipeline that we downloaded. So pipeline. So we can just apply our list to that. Okay, result. So we get a list of entities. So which means that we have this dictionary for each item, for each list. They are still dictionary. So this is the document part of speech and stamps for the first sentence. If I want to get the same for the second sentence, I get this one, etc. Which means that you can manipulate as much as you can. So you can just fit 100. If you have 1,000 sentences and you want to use pre-trained pipeline, you should convert it into the list and then use pre-trained pipeline. Otherwise, you need to loop through again and again, which is very slow. So you can just use that. Okay, so let's have a simple sentence. Peter Parker is a nice guy and lives in New York. So I'm going to use this example to show you how to use full annotate. So far, we have been using .annotate, right? .annotate. But right now, I want to show you how to use full annotate. Full annotate means that you get the metadata as well. Right now, it's explained document DL because I assigned this before. If I apply full annotate, let's apply. Okay, let's text and apply. Now I can check what's inside. So you will get this kind of ugly output at first, but they all have some purposes and the meanings which you can access. Let's access. So because it also covers the starting and ending indices of each entity that we extract. Like a Parker starts with 6 indices and then ends with this indices. And that is the first sentence, and the confidence level is 100%. So which means that you can get metadata of the extraction process. So let's see the entities, like the entities extracted from this text. You see, Peter Parker is an entity. It's the person entity from sentence 0. And it's the chunk 0, like the first entity from first sentence. Second entity, like a chunk from the first sentence, is a location, New York, and starts with at position of 40 in my text. Like, for example, text is a string, you know. So when we want to write this one, you see, I get the indices of each tokens. So you don't when you want to know the position of the desired entities. So let's create a data frame. We can just create like a loop through. Okay. When we loop through, we will end up with this one. So it will just collect all the entity. So how am I going to reach the entity of each? Like this is these are the entities, right? If I want to reach the entities and its starting indices as a table, if I do this, I will get one annotation. So if I want to reach its result parameter, I can use just this one. So that's why I'm using for loops here to collect the result and entity. And let me show, if I want to get the entity, like I can just copy here. So like the first annotation, metadata, and the entity, it's a person. So which means that I can just collect this in for loop, and I get this table, like the chunks and the entities list. So if I want to do some more details as a pandas data frame so that you can share with your colleagues or do some machine learning on top of that, assume that you want to get the tokens, start and end indices, part of speech, and NER text of a given text. Okay, so when you do that, when you run this, you can just build the same for loop. At this time, you can just get like the sentence, which means metadata sentence is the sentence ID. Result is the like X is right now in zip is this one, which means that the sentence of this token, first token, the result of first token, like the token itself, begin indices, end indices. The second one is part of speech, so I can just use its result, etc. So and I can end up with this table. Let's run this. So I will end up with sentence ID, token, start, end, part of speech, and NER tag, just by using full annotate. If you just use annotate, you cannot know the sentence ID or start and end indices. If you want to get more detail, you should use full annotate. So let's use pre-trained match chunk, which means that if I want to extract some pattern, if I want to say that I want to extract all the nouns coming after the or a, like a determinator, or I want to get, for this one, for example, I want to extract a pattern which is like an optional, like the a, dt is in part of speech. This is determinator, like a the and a, followed by any number of adjectives and noun. For example, if you want to extract a blood cell, which means that like a blood cell, so they're all noun. For example, if you want to get like a yellow car, yellow is adjective, car is noun. So which means that you can just define these rules and then you can extract some desired format, like desired chunks from your text. Let's do the same here and then show how it works. It's again, we just load math chunks. Okay, it's downloaded. So I wanna, this is my sentence. The book has many chapters. Okay, so this is, I want to extract. So when I run this, I should end up with this one because this fits the pattern, like the book. So it fits right now. So I should be able to get one single chunk out of this one. Let's run this. And here's the result. Like the chunk, extracted chunk is the book, because this is the only pattern that it fits. If I had another pattern, if I want to like number and then nouns, if I want to write that one as well, like define like plural plus noun, I would get many chapters as well. So this is very useful for if you want to extract some clinical text from your large corpora. Okay, so our chunks are just one chunks. Okay, the little yellow dog barked at the cat. So we can now do the same for this sentence. And I should be able to get two chunks right now. As you see, the little yellow dog fits the pattern. The cat also works because it's the same pattern. It's like a regex with part of speech. It's very useful. Okay, in the next lesson, next hour, I'm going to show you how you can extract some desired, like you can extract some like cardiac, starting with any chunks with cardiac or insulin, something like that. Let's do the same for, let's try to extract some exact dates from referential date phrases. If I want to say that I saw him yesterday and he told me that he will visit us next week. So there are referential dates here, yesterday and next week. So if I want to get the exact date using today's date, I can just use match date time pipeline, pre-trained pipeline, and then annotate. When I annotate, these are the dates extracted from this sentence. It's at first find the time entities, not the entity. The date matcher is using regex, by the way. So to be able to extract complex dates, you need to use some NER plus date matcher, which we can discuss later. But for now, for the first lesson, this is using regex and some rules on the backend. So the yesterday is converted to yesterday's date. And like this is the 15 is the next week, and the 7 is the yesterday. So how should I know which one refers to which one? I can use full annotate. When I use full annotate, I get the start and end indices, and then I can find which one refers to which one, right? Like yesterday starts with 10 and 18, between 10 and 18. Which one is 10 and 18? You see this one? It's 10 and 18. So which means that you can map this one, this token with yesterday, if you wanna investigate which one refers to which one. Okay, so
should it be?
Okay.
So should it be 2020 April 14? Because we are talking about yesterday, right?
Yes, yesterday is.
Sorry, next week.
Next week is 5765. Okay, next week. It is, next week is 5765.
Yeah, but relative to yesterday, it should be 2024-14.
Yes,
the sentence says I saw
yesterday.
Yesterday.
Yesterday is 7th of April.
No, not yesterday. So I saw him yesterday.
Okay.
He told me that he will visit us next week.
Okay, you want to build something like it will take the next week from yesterday, right?
Yes, yes.
No, this is as I said, this is a rule-based right now as an intro. So if you want to do something like that, you can just try to find any date. You can write a rule as a developer. You can do something like that. I found the date of yesterday, and then there's another referential date, like the date of yesterday. There's also another referential point, this one. So I can check the today's date. It's 8th of April. There is a 1 day difference between this one and 8. So I will subtract 1 from the other one. For example, I did something like this for another client project. For example, we were trying to get the dates of some metastasis. Our data extractor was extracting the dates using today's date. I used the documents date to normalize that, to find the difference between documents date and today. Okay, so it's up to you how to manipulate it later on. Okay, so for sentiment analysis, if you want to just get a sentiment, this is a pre-trained model. We will release the much powerful sentiment models in the upcoming weeks, but for now, this is what we have, which is trained on some common public data sets, and then you can just download this one. It's just 5 MB, and then you can just annotate. The movie I watched today was not a good one, so I can get the sentiment of this word, this phrase. It's negative. You see, if I do full annotate, I will also get some much more detail, like scores as well. Okay. So this is the first notebook. We are done with the first notebook. Now I am skipping to the second notebook before going to the slides again. The second one is text processing, which is very cool process that we are going to discuss right now. You will see all the steps that is needed for any NLP projects, and we will use all Spark NLP annotators and transformers in a pipeline. So we will do real Spark right now. If you are ready, we can start. It's already 1 hour, I guess, but we are not done, so we need to cover this one. We can have a break if you want, or we can just keep going. It's up to you guys. Okay, I'm moving on, I think, to be able to cover everything, because we are doing the Q&A section one by one. And I'm assuming that you already run that on your own, on your end, right? You also try to do the same while I'm discussing, right? And if you are not doing, please do, because it will be helpful if you end up with if you bump into some issues, so that we can discuss. Or you can just manipulate my code.
Training instance available.
Sorry?
So how long can we use this training instance?
It's 12 hours, but when you don't use it for a while, it's sleeping. It's provided by Google. So if it sleeps, you will see that it will not be running. You can just reconnect again and then start using again. So if you reconnect, you will lose some local file if you download local variables, like ending the kernel, like killing the kernel in Jupyter. It's the same. If you download something here, which we are going to do right now, if you download something and if it dies, if you want to restart this instance, you will need to download again. Sometimes it just sleeps, resumes from your previous session, so you don't lose any variables. Sometimes it all depends on Google availability. Okay, but it's totally free. So right now the first cell is done, which means that Colab is ready to run Spark NLP codes. Okay, annotators and transformer concept. You can read this from the article that I shared at the end of the slides, like Introduction to Spark NLP Basics and Foundations. So I'm not going to cover that right now. There are some verbal details here. What is annotator? What is transformer? If you want to feel good in Spark NLP, you should definitely read that article in medium.com. I also shared at the end of the slides. So let's start with, but basically we call all these steps in a pipeline as an annotator, and then annotators are even we fit or get transform means that like transform my data from some pre-trained models. When we do annotate, we basically do some transformation because it's already fitted. When we want to fit a new model, we use annotators. So these are the bases. But when you read that article, you will learn much about this concept. So let's download. You can download not download. I just download this to show you the annotators inside Spark NLP. But as a quick tip, you can use CLI commands like you do in Jupyter, like with the exclamation marks. I think in Databricks you use % and sh to do the same. In Jupyter Colab you can do this one.
Yeah, just FYI, I mean, it was recommended that we shouldn't use the sh, instead use DB utilities in Databricks.
Yeah.
So that it gets installed on all the worker nodes as well.
No, okay, I just mean that if you want to download some external data, like data set, or externals like image or PDF you want to download here. Okay. You want to download to this instance.
Oh, okay.
There's an annotator CSV file from GitHub. I have the link, public link, so I can just download it and it will be on my disk. You see, this is my local. When I do this, let's do this. Refresh. It's here, which means that, for example, I usually do what I do. I have a large image files or text files in Google Drive. I connect Google Drive here. I download it, and then I connect my drive here, and then which means that I can use my drive, Google Drive, as a disk for my notebook, which is very convenient.
Okay.
Okay. So why I did this, to show you some. This is a table that I also shared in the article, like the list of annotators in Spark NLP and their meanings, which means that like this is tokenizer, normalizer, stammer. I think we already covered this in a pipeline, but right now we are going to use them one by one. We will have around 30 different annotators, some of them fittable, some of them just transform. So let's start with, this is the same image that I shared before, like how the pipeline's working. So we will just use these annotators inside the same pipeline one by one. We will just take the output of one annotator, use as an input to another annotator, like a building blocks. So we just take tokenizer, put on top of sentence splitter, and then we get the stammer, and then put on top of tokenizer. And then we say that take the output from tokenizer and use as an input in the stammer. So which means that you can do anything you want. It all depends on your imagination. So you can manipulate this pipeline as much as you want. So let's start Spark NLP session. This is already started in Databricks, by the way. So it's right now starting my Spark session using PySpark and our jars and the packages on the backend. Now we will get into how to work in Spark, PySpark. So I hope that you also covered some basics in PySpark. It just takes a few hours. If you have no idea about PySpark, you can just Google it like medium.com, and then you will get some basic PySpark instructions, and then it's the same. So we are using the same as well.
Quick question here. So while you're importing this Spark NLP, is Jon Snow libraries are also getting imported? Because I have not seen I've not seen a code that installs those libraries.
Okay, so we have the jar files that's running when we run Spark NLP.start. It starts a Spark session using PySpark. Let me show you. This is our Spark NLP repo.
I see.
Okay, Python. So when you have the Spark NLP Python, this is the folder that you have on your local library. So in init, when you run start, this is what happens on the backend. Okay.
Okay.
So it starts a session using all your CPUs with 16 GB of driver memory. And then, for example, if you select GPU version, the relevant packages will be downloaded from pipeline.
Okay, got it.
So when you do the same for the license version, it will also install from the license. Okay. So that it hides the ugly part of that starting the session. But it's nice that you asked this because I wasn't planning to cover this, but let's cover. If you want to do, if you want to start a session with more memory, or just using half of your local processors, you can create your session manually. If you get an error like maximum buffer size in Cairo serializer is exceeded, you get an error, for example, in the future, you can just start your session with more buffer manually. But this is a default session that we create with Spark NLP.start. Okay.
Got it. Thank you.
Okay, perfect. So we have the same sentence. Peter Parker, I think I have something to do with Spider-Man. Peter Parker is a nice guy and lives in New York. So if I want to get a data frame from this text, I can just create this one, like a create Spark. Spark is my session, which is already started here. So if I want to create a Spark data frame, I'm using my session and then create data frame and use my text like a one single text. If you want to get a data frame from one single text, this is the most easy way to do that. So at the end, I have Spark df, like a so if I like truncate in Spark NLP in PySpark, if you truncate like true, it will get the exact sentence. This is short sentence, so you will get the all. If you say, if I say true, it will just concat sum, just for the cosmetic purposes, truncate here. So this is a one row data frame, which means that I can now use this in Spark pipelines, Spark NLP pipelines. So let's create, you can also, I didn't run this, for example, assume that you have some pandas data frame. Okay, this is just df. No CSV, like you read your CSV and assign as a pandas data frame. And now you want to convert into Spark data frame. You can do the same here, which is very easy because when you have the data frame, large data frame, it's on your memory when you use pandas. If you have pandas, you can convert it to Spark. It will still be in the memory. But if you have CSV and then read as a Spark data frame from disk, it will be distributed data frame, which is the nice part of Spark itself. Okay, so we have the Spark df, one single row. And now I want to download some sentences from GitHub so that we can use, like I'm planning to use, I have like 5 sentences. Instead of writing one by one, I will just download it. Okay, now I can read this text into Spark data frame, which you will use most of the time because you have a clinical text or some text that you want to use, that you want to process. And you can just create data frame from that text, which means that every line, when you read single text, every line in that text txt file will be a new row in the text. Okay. So if you want to read a whole bunch of text files from disk, assume that you have 1000 clinical notes in one single folder, and you want to apply a large pipeline on top of that. And you want to create a text file, like a Spark data frame, using all these text files, which we do all the time. And I'm sure that you will do as well. So you have a local folder here. We say that whole text files, like read all the text files inside that folder. And then these are the column names, path and file content. So at the end, right now I'm on the one single txt file in my local, right? As you see, I just have one single txt file. So when I do that, it will create a one single row. If I would have like a 1000 texts, there will be some 1000 rows here. So when I run this, I will get a data frame, which is very convenient for the next steps, because when I do that, for example, I have 1000 text files, I do this, and then I keep track of with the path column so that I would know which text corresponds to which path. Okay, right now I have it. Let's take the content of the first row. So which means that one single text file is right now one single document with, you know, it didn't read line by line. But the first version did line by line because I read text. But here I read whole text files. So whole text file, single text file converted to single entry. Right now I have the Spark df. And now I want to start use Spark NLP annotators one by one. Let's start with document assembler. Document assembler is the entry point to any Spark NLP pipeline. So you define some, like input column is, you define the text column, like the column that you want to process from your data frame. Right now we have this one, and it's the file content here in the Spark DF, right? So if you want to process this one, I will use file content as an input to my, did I run this? I'm not sure. Okay, let's run again. So I will just use that one as an input column. So which I will tell Spark document assembler to use file content column as an input, and then give me an output column. I will just write anything, and I will say that, okay, do some basic cleaning. Like if some of the texts there are too much like spaces between the sentences, like some tab characters between the words. So if you want to do some text cleaning while loading, you can use these options here, like in place full, shrink full. Let's do, it's easy to understand while coding. Okay, we import document assembler is coming from Spark NLP.base. Okay, so we define that at first. We say that, okay, document assembler variable is document assembler from Spark NLP base, and its input column is text. But right now, when I apply SparkDF, it will give error because it should be file context, right? File content, because I want to use the file content column. But let's keep it simple and then read that one again, not the entire directory. Okay, let's use text column. You understand what I did, right? I'm assuming you did. Okay, I have the text column as an input, and I'm setting the output column. Why do I use this notation? Like instead of writing the same line in Python, I will just like a backslash. I split my code in multiple lines. So output column will be document. So this is another document type column, which I call document right now, and do some basic shrinking cleaning right now while reading this one. So when I do that, I will end up with document df, which is another data frame. Right now, I ended up with a new data frame. You see, I ended up with a new data frame with document column. So it appended a document column next to text column. Right now, all the annotators in Spark NLP can be applied to this document column, because right now it's understandable. It's in a format that is understandable by Spark NLP from now on. Now I call it docdf. So what's inside that docdf? This is the schema of that document df. I have text and document column. Document column is a struct type. In Spark, we have a struct type column. All the metadata is already there, which means that you can access the metadata as well. So I'm also going to show you how to get rid of this metadata if you want to just get a simple pandas output. I will also cover them as well. So since I have docdf right now with two columns, if I want to get the start and end indices of each document, I can just reach this subcolumn, subfield, by using dot notation. So in pandas, in Spark data frames, we use select. In pandas, we use just prerequisites, but in pandas, in Spark, we use dot select. And it selects, for example, document, like select the result subcolumn from document column. So like the result of the document, and then begin and end, which means that it will get the begin and end indices of the document itself. When I run this, I will get each entry as a list, because this is result. Result in data frame in Spark NLP outputs are always a list, so that you can manipulate later on. So it's a architectural design, and we have the begin and end indices for each one. So let's just take the first one. You don't want to see the table like this view, and if you want to get the take in Spark, I assume that you already know some Spark. when you load a large data frame, you don't need to load it to like entire data frame to disk. So that's why we just take the necessary parts of data frame whenever we need in Spark NLP for the efficiency. So when you take, it will just take the first row. Okay. So document result take, when I do this, it will get the result attribute of the document column. So I will get this one. So let's explode. Explode means if you are not happy with this notation, which I was not happy at the beginning. So we were trying to find a solution, and then Spark NLP, PySpark itself has already this explode function for that. So which means that instead of trying to get this raw data, you can just explode your entire data frame. You can Google for it later on how to use this, but you just take the document and explode it. Because document is a struct type column, you can explode and then get all the sub columns as like a flattened, like a begin and result, you see? So you have, and then you can just convert it to this pandas later on. Okay, now we have the document assembler, which is the entry point. It is doing nothing except taking your data into Spark NLP. Right now we have a document df, which is ready for Spark NLP annotators. So we can get NERs, we can split the sentences, we can get spell checker, etc. Because in pre-trained pipeline, we were just dealing with single text, single strings, because they were all fitted. And they were all just a single text. So if you have a large file, this is the only way that you can use Spark NLP features. So we have the annotators. So we import everything from annotators. And then we fit the document column coming from the document assembler. So this is the document column that is coming from previous annotator. Previous annotator is document, right? So this one. So I at first get the document column. Now I want to get each sentences, like I want to split the sentences from that document column. So I use the input column as a document and the output column as a sentences. Okay, and now I want to, like I defined, now I want to run this on the documents df. Okay, so which means that already converted by doc assembler. So now I'm going to get the sentence detector. So it's just transform, because sentence detector is a transformer itself. In the annotator CSV table, I put some plus and minus to let you know which one is transformer, which one is annotator. So when I do this, I append a new column, which is sentences. The sentence column is coming from here, output column. Okay. So, which means that create a new column named sentences and put the sentences inside. So I have a list of sentences here with all the metadata. It's the sentences are split for each entry. Okay, let's do this and then run this. Now let's see the first sentence. Okay, in the first one, we have just one single sentence, right? So if I want to, for example, in the third row, I see two sentences. So if I want to see like the, let's say, show me the first three. Okay, so as you see, John and Peter are brothers. This is one sentence on the third row. This is sentence 0. Now I have another sentence. However, they don't support each other. It's the sentence 1, which means that now I have that metadata like a sentences inside that column. So if I want to reach the sentence by indexes, I can do that easily. So assume that I have this text. The patient was prescribed 1 capsule of Advil for 5 days. This is a multiple words, like a clinical verse, sentence, okay, text. And now I want to apply all these steps. Okay, I want to get the sentences from this one. You see there are some like bad formats here. So let's do this. At first I create a data frame from this single entry, and then without doing this, you can also create a data frame from list of sentences, you know, like if you split your text, you can also create a data frame like this, but we will not do this. We don't need to do that. Okay, let's just show it. We have one single row because we have one text and then we created that one. Now I want to apply document assembler at first and then sentence detector, which means that I want to get the sentences from this entry. At first I transform on document assembler and then I get the output and then transform in sentence detector. Now I have three columns, like document column is created here, sentence column is created here. So if I want to get the sentences one by one, which means that if I say sentences.result, I will get a list of sentences from the first row. You see, the patient was prescribed one capsule. This is the first sentence. This is the second sentence. Yes, you see, this is the end of the second sentence, and this is the third sentence. So, if I want to show as a if I want to see in a table format, same actually. I think we are done with the sentence detector right now. Okay, so if we had like a 3 rows, we could have some much more detail, but right now we have 1 row. Okay, for the tokenizer, if you want, right now we split our text into sentences. Now we want to get the tokens from each sentence. This is the next step, which is the most important step actually, tokenizing, which we call it. There are too many parameters here that you can manipulate, but you can easily call it with the default parameters like tokenizer. This is the same Spark NLP annotator. It's coming from there. So we take the document column and get the tokens, or we can take the sentence column. We usually do that, but most of the time I will just skip sentence detector during this tutorial because no need that for, because I will just use the simple text files, text data frames. So I will just use the output of document assembler as an input to tokenizer. So you can use the, if you want to tokenize by sentences to get the sentence instances as well, we can just feed the sentence here as well instead of document. But right now I'm just going to feed document column, which is coming from document assembler. Let's do this. Now I have Peter Sparker is a nice guy and the same. I added some much more noise to show you something, like some different attributes of tokenizer. Because when you see that this is, when you split in Python, we usually do, let me do something. If I have this one, and if I just think that, okay, I can also get the tokens by splitting by space, right? But if I do this, this one will be 1 token, which I don't want, like parentheses, or like the exclamation mark will be, because there is no space between them. So when I do this with Python, you see these are all tokens, but these are not tokens actually in NLP purposes because this is not a word. We have some unwanted chars here. So in tokenizer, that's why we have some other parameters that we can set. As a default, when you run this one, and then run tokenizer on top of document assembler, you don't need to deal with that parentheses or etc. Okay, let's do this and then see our tokens. You see Peter, Parker, parentheses, Spider-Man, parentheses. So, which means that we get all the tokens one by one, and it's split here as well. How does it do that? Because there are some default rules that we apply for that. If you want to change that rule, you see email is already detected. It's the 1 single token, an exclamation mark. So if I want to say that, set split chars, like if I some certain pattern that I am aware before processing, and I want to get the tokens out of that pattern as well. I know that there is a hyphen between e and mail, so I want to split this as well while tokenizing. So I can just say that I have some words inside my text, which is splitted by this one. So ignore this. So which means that split them as well. And if I can also say that these are the context charts, so do not drop them. So do not, because do not do this one. Okay, I can say that, okay, these are, do not ignore these ones. These should be wherever they are. So I can just define these. Or I can also add exceptions. I can say that New York, do not tokenize New York, because New York by itself is this is enough for me if you say. Okay, for example, this is useful if you have some pattern, like a 1 milligram, for example. You can just say that it will not be dropped, but it's much more complicated than this one actually. So if we do this with the new tokenizer that I just defined and run this, okay, I think I made a mistake here. Even though I defined this one, it's here. Okay, email is splitted, as you see. Okay, so if I say that, let's remove this one. You see, so I told them that ignore this one because I overwrite the default params, and I said that this should be separated, like exclamation mark, question marks, but parentheses should stay where they are. So I removed them. So I overridden the default parameters with this one. So Spider-Man is here again with the parentheses. Okay, so you can just check the full documentation to see what I mean. Okay, let's do, right now we have been doing this by adding one by one. We were using document assembler and then sentence detector and then tokenizer. Let's use this inside pipeline, Spark ML pipeline. So no need to worry about transforming again and again, like we do in scale-on pipelines. So we can just use PySpark pipeline. This is the pipeline coming from PySpark itself, not Spark NLP. So we use document assembler at first, and then sentence detector. For example, if you want to get the tokens from a given data frame, you can say, okay, use document assembler, sentence detector, and then tokenizer, and then put them inside a pipeline. These are the stages of the pipeline. So, and then I can just fit on an empty data frame. We usually fit on empty data frame if there is nothing to train. Right now, there is nothing to train, right? Because I don't have something to train, like tokenizer, sentence. I don't need to train because they are all rule-based right now. So, which means that I can just fit on, because all pipelines needs to be converted in pipeline model in Spark. And it's the only way to do is to fit on some data frame, which we can fit on anything. I just select empty data frame. So I create an empty data frame and then fit. So right now I have a pipeline model, which I can call, which I can name any way I want. And now let's read the sample sentences txt file again into a data frame. At first, let's create this pipeline model. Let's just create it. And then I'm reading the sample sentences and I created data frame. Now I want to transform this data frame with this pipeline. Okay, so which means that I will just use one single line, and this data frame will go through all these steps by itself, like document assembler, sentence detector, and tokenizer will be done in a pipeline. So let's do it. Now, as you can see, I had just one column, text column here. Now I have the document column from document assembler, sentence column, and token column from tokenizer, which is all done in one single line with a pipeline. When you want to print the schema, you get a huge constructs here, like a struct types. So you can reach one by one any way you want. So let's take the sentences. So we use the result attribute of sentences column. So which means that I have one sentence in the first row. In the second row, I have one sentence again. In the third row, I have two sentences. It's already like a list of sentences, you see. So if you get the tokens as well, you see all the metadata, all the result. If I just, for example, if I want to say that to get a token result, and You see, like a list of tokens for each. So, for example, sentences are also like a concatenated list, like one single list, because this is a token column coming from. Okay. As you see, document is fed into sentences. Sentences fed into tokenizer. Okay, so normalizer. Normalizer is used to clean and normalize your text data. For example, if the most common use case would be removing all the punctuations. Okay, if you want to remove all the punctuation from your task, you can just define a pattern, cleanup pattern, and then remove. For example, this is the list of punctuation. If you want to remove this, how do you do this? Python, we just loop through char by char, because each string is a list of chars actually. So, and then we drop if that char is not in this list, right? So instead of doing this in normalizer, what we do is we take the token column, because we normalize the token column. We normalize each token, each word. And as you remember from Spider-Man, we have the parentheses. If we have the desk, those kind of issues, and we want to remove the parentheses, we can just use normalizer as well. If we fail to separate these unwanted chars in tokenizer, we can still do this in normalizer, which means that let's write regex here. I am assuming that you know some basic regex. So this says that just keep alphanumeric chars, right? Like the words and the letters and the digits. Just keep them, which means that remove all the punctuations. The rest of the other than anything which is not alphanumeric will be removed. So this is like in Python we say like we look through in a text char by char and then say that if E is alnum, there is an alnum method in Python, as you may remember, like yeah, assume that I have this one. I have my text, let's say, an exclamation. So if I say that for E in I in my text, if I is unknown, you see, since this one is not alphanumeric, it's dropped, and I can just this is what we do in Python usually if we want to remove some unwanted chars. You see, now I cleaned that, but it removed the space as well. So which means that instead of doing this, we can just set up some patterns in regex, in normalizer, or you can do the same in Python as well. But I just wanted to compare one to one. If I don't set clean patterns, it will only keep alphabet letters. So it will also drop the digits as well. So if you just want to get the tokens with the letters, not digit, no digits. If you want to drop all the punctuations and the digits, which we usually do in any text classification purposes, if the numbers are, because when you try to convert some numbers, like encode some digits, it's useless because it doesn't tell anything about your text data most of the time, if you are not using them as a scalar feature. So long story short, we have the token and then we have the normalized column. So we create a new column which is called normalized. Now I also want to lowercase all each token and then clean all the punctuations. Okay, so I run this one with a normalizer. And now I want to build a pipeline here. So here's the pipeline because I already have the document assembler and tokenizer defined. So I can just add the normalizer at the end of the pipeline and then fit on an empty data frame. So, okay, I need to change something. No, because I need to define, I need to give document because I just skipped sentence factor, okay? In the previous steps, the tokenizer was using sentence, but right now I want to use the document coming from the document assembler. Now I run this one. Now the token will be converted to normalized column. Okay, it run. Now I want to transform my data frame, Spark data frame, which means that I will have 4 columns. Text, document, token, and normalized. So the normalized column is created using the token column. And let's see the result of normalization. You see, Peter is a very good person. You see that like lowercase, I have no punctuation here. All the punctuations are dropped. How to make sure? You can just write, do the same, and let's see the token at first. You see all these punctuations were in token, and like don't, you see the punctuation again, and however starts with H, you see. So we create a list of normalized tokens with the help of normalize. Why we do that? We usually take our text for text classification, do some text processing. These are the text processing actually that we talk about. Like we clean, and then we get a clean version of the tokens. Now we can remove the stop words. You remember the stop words that I was talking, like removing some useless tokens that has nothing to do with the true meaning of the text itself. If you want to classify sentences, like if you want to find the sentence similarity between 2 sentences, Peter is a very good person, or Peter is not a very good person. So the true meaning, you can just say that, okay, keep the negativity. Okay, this is not a good example. Let's say Peter is a very good person. They are very good people. Okay, which means that is and a are stop words. It will be dropped. In the other example, you will have the they are will be dropped as well. So which means that you can find the sentence similarity or text classification purposes. You need to, most of the time we need to drop stop words. But with the latest development, like advances in Spark, like in NLP, using transformers or the BERT architecture, we may not need to remove them. I will explain them in the last session today for text classification session. Okay, let's remove the stop words. So I just defined stop words cleaner. This is another annotator coming from Spark NLP. And I want to clean the token column, which means that remove the stop words from the list of tokens. So, and give me another column which we call clean tokens. And then also do not pay attention to case. So you can stop like lowercase or uppercase, it doesn't matter. So you can also set some stop words. We also use some default stop word list. Like it's we are using the stop words coming from Spark. But you can, if you have clinical stop word list, you can just read it from the text and create a text list and then set here, which I usually do in the real projects. I prepare a custom stop word list and use here. When I do this one, the default stop word list will be overridden and this will be used, and it will not be, like just the ones in this list will be dropped. Okay, so let's do this and drop, like build the same pipeline, but instead of tokenizer, let's use stop words cleaner. Okay, we can also use normalizer here, right? If I change this one from normalized, right? Which means that clean the tokens from normalized. So let's not do this. So let's clean from the tokenizer itself. Okay, it's fitted. Now I read the sample sentences from disk again. You don't need it because I didn't end the session, but if the session kills, you can, or if you lose that one, you can just read from the text again. And now you see the clean tokens. So which means that right now, if I want to, like, let's copy paste from here. The column name is clean tokens. You see, Peter is a good person. Is dropped. Since punctuations are still there because we didn't clean them with the normalizer, we dropped normalizer pipeline. We just cleaned the tokenizer column. So which means that life, my life in Russia, you see, so my is dropped, in is dropped, etc. So I have the clean version. Now I have the clean version. What if I want to assemble all of them? Like I tokenized, normalized, cleaned, like removed the stop words, and then now I want to combine all of them again, like assemble all of them again, so that I can have one single sentence with a clean sentence, not with drop, like stop words dropped, punctuations dropped, digits dropped. Now I want to have the clean version of this tokens. So which means I can use token assembler. In token assembler, like for example, I got the document, like I fit my document here, I split my sentences, then I tokenize, I normalize, I clean the tokens, like clean the stop words. Now I want to assemble back all the cleaned and removed, the final version of the tokens. Okay, I can just create this pipeline, like token normalize. So it's like an intuitionally, it's very understandable, right? Like we feed a text and then we apply all these steps. Now and then I put all this step inside the pipeline and then fit on an empty data frame and then transform on my Spark data frame, which means that I will just give one column and I will end up with all these columns. Okay, I run this one and I ended up with this one, which is very fast. Now all the steps are done. So let's access each attribute. Let's say I want to see the text, raw text, and the clean text next to each other. You see, Peter is a very good person. So is a and dot is dropped and then assembled back, right? Peter, good person. This will be like life, Russia, very stop words as well. Interesting. So life, Russia, interesting. You see, if you also apply some stemming, you would also get the root version of this one as well, which we will do right now. So if you want to explode, because you see that these are lists, so it's hard to access maybe in Python. It's a list column, so you can just explode that as well, and then you can get this. Very nice, right? Like a begin and end of each sentence, clean sentence, and the original sentence in this index. So which means that you can just map this table to any other row table so that you can compare or do some processing later on. Okay, if we hadn't used sentence detector, right now we use sentence detector, right? We use sentence detector in our pipeline. If we hadn't used that one, like remove the sentence detector here, and then I just fed the document to the tokenizer instead of sentences. So which means that, let's run this one and explode. Okay. Okay, so explode is coming from the PySpark itself. So right now I have, because I didn't split the sentences, they are all 0 sentence. So, and I got the entire document connected, like assembled back instead of sentence by sentence. Okay, let's do stemmer. Stemmer, as you can remember, we get the base stem of each word. Because this is like interesting, you see, life, Russia, interesting. So this is still something, you know, like some ing here, suffix here. So if it says interested, interesting, some other forms of suffixes, so we can normalize that with stemmer, so that we normalize our text as much as possible. So we fit the tokens column to stemmer. Now we have another annotator, which means, so let's just tokenizer and then stemmer in the same pipeline and get this one, and let's see the result. You see, Peter, because I didn't remove the stop words, they are still here. Interested is interest right now. As I mentioned in the slides, when you use stem, you lose the real word. If I had used lemma, which I'm going to do next, you would get B instead of is here. So which means that I get the base words, which is the simplest undividable part of a word, actually, in English. So let's explode, like not an explode, but let's, because these are a list of tokens, we can get each token and stem version. Like token, Peter is E, like per very is converted to this one. This is the stem of very. So let's do the lemmatizer. I'm trying to finish this part. Let me see. Right now I need to cover all this, but I have 10 minutes. After 10 minutes, we will have a break before getting into NER and text classification. Okay, so let's use lemmatizer. Lemmatizer, as I mentioned in the slides, is using a lookup table. If you are using untrained version, we also have a trained version I'm going to cover next hour. So if you have some lookup table for the lemmatizer, you can use that one. This is a format. You can check this file. Let's download it. Since it's not in Colab instance right now, I'm downloading from some repo that I found. And then let's define lemmatizer. Okay, lemmatizer is ready. Now I want to get the stem and lemma together. So document assembler is always there. Tokenizer, stemmer, and lemmatizer. And I put the lemmatizer inside at the end of the pipeline. Let's run it. Freetom empty, get transform on Spark data frame, and then let's see the lemma results. You see is converted to B. Interested converted to interest. So I usually prefer lemmatization, by the way, because it's easy for word embeddings as well, because it should be an understandable word in the vocabulary. So let's see 3 columns at the same time in like a pandas. By the way, as you can see, this is Spark data frame. You use some like expressions, select, filter, etc. When you do to pandas, it's converted to pandas. Let's do this. And let me show you type of this one. Okay. Now it's pandas. Okay. So sometimes if you want to do some basic manipulation and you feel comfortable in pandas, you usually do like convert into understandable tabular format and then convert to pandas, so that you can save to disk as a pickle or CSV or Excel file and share with your colleagues, or do some stuff in sklearn, or do some visualization, which is very easy to do in Python compared to Spark itself. So n-gram generator, n-gram, which is like an n number of tokens concatenated together. For example, yellow car. If you want to extract, for example, Peter is a very good person. If you want to get b-grams as well, like Peter is a very, you can also do this with n-gram generator. So we define, for example, here I say that set n to 3. This is very useful for the textual function because when we try to get the TF-IDF in NLP, we usually apply some n-grams, like 2 to 3 grams, to find a pattern, to help the model find the pattern, so that we find some obvious pattern inside the text that is usually used together, like some tokens. Like, let's apply this one. And right now, as you can see, this is the original, like a 1 token, like a unigram. Now I have the bgrams here because I told 3. 3 means that take bgrams and 3 grams. So I got the 2 bgrams. And then now I have the 3 grams, my life in. So it's like a sliding window. Life in Russia. In Russia is etc. Okay. I think it's very simple. So I'm just skipping. Text matchers. Text matchers will be very valuable for your work, I assume, because usually clinical guys try to extract some words, like a known words, by checking lookup tables. They either use regex or simple find in Python. So in order to do this in Spark NLP on large corpora in much faster and efficient way, we have the text matcher. So let's download some PubMed dataset. This is a PubMed dataset. I think you're all aware of the PubMed dataset. This is a small sample from PubMed dataset that I just downloaded from our repo, which is very free. So let's convert it. This is how I read CSV file into Spark data frame, by the way. I read, this is the required portion. So I do some cleaning here, like I remove the rows that the AB column is null, like null, and I rename that column as a text, and then I drop the blah blah blah. So I will end up with the text column, just one single column with the PubMed articles dataset. Okay, it's reading from the temp. Okay. By the way, if you get some errors in Scala, in Java, since this is using Java as well, the error might be frightening. Okay, horrible sometimes, and it's very. Don't fooled by the length of the errors, because sometimes, most of the time, they are very easy. You see, just this one. In Python, we just end up with small, like a short errors, but in Java side, it's very long. So it just says that path doesn't exist. So which means that I had a typo here. So I need to remove this one because I downloaded to my local here. You see, PubMed sample. So I don't need to use temp folder. Okay, I changed this one. Now I have. So it's that CSV file is read into Spark data frame. Now I can see one text row. This is a long text. Okay. Now assume that I want to find all these entities from each text file. Like, yeah, but so I can write this. You can have like hundreds lines of target words, target n-grams, target phrases. And I just created a list, random list, and then wrote into clinical entities txt file. Okay, you can prepare this somewhere else. Now I want to use text matcher to find these entities from the entire corpora by using clinical entities txt file. It needs a physical file, so I wrote this list to do here, and then now I want to extract all these entities from my text. So let's do this. Okay. Now, to make it faster, let's just check the first 10 rows. I can select first 10 rows, like limit 10. Otherwise, it will use, because PubMed df, let's check its length. It's like 7.5K. So no need to wait for it. So let's just process the first 10, and then get the matched entities. You see, these are all the matched entities from the first row. Let's see which tags are in which part of the document. We can just explode and then begin and end using the metadata, which means that diabetes mellitus are between in this instance on that text. Okay, when I use slicing of that text, that one single entry, I will end up with this one as well. So which means that it's found. So let's do the same with the regex. Instead of trying to use a list of, if you have a known pattern, if you already know the pattern that you want to look for, you can just use regex matcher. You can create this in the same manner. You can create a rules, and with the explanation with the comma. For example, right now I say that find everything starting with renal, like renal X, cardiac X. So, and like renal, and then the coming after renal. So, and the cardiac. So I have two rules right now. I wrote these rules to txt file. You can enrich this regex as much as you want. Now, let's build another pipeline with just document assembler and then regex matcher. I'm not, I think you have realized that I'm not using tokenizers in text matcher or regex matcher. You can just apply this to entire text. So let's say match all. This is the same that we do with regex in Python. So output column will regex matches, and then use these rules from that txt file, which is separated by a comma. So let's run this. You see, these are all detected from, sorry, okay. These are all detected from the third row has these matches. Let's see, let's drop the empty ones. Empty rows, like the rows that has no desired matches, and show the rest. Okay, which means that right now this is the original text. It's abbreviated here. It's a very long text, and these are the matches that I got from that text. So if you want to find some specific text or specific pattern out of your large corpora, you can apply this one as well. Okay, the last one is finisher. Finisher is right now we are getting, you see, like matchdf. Let's print its schema.
Quick.
It's very ugly here.
Quick question.
Okay.
Like you said, you showed us doing stuff with text matcher as well as the regex, right? So why would I pick text matcher if regex is doing the same thing, or what is the difference that both are doing?
Text matcher, in text matcher, you know what you look for. You say that, okay, I am looking for diabetes mellitus. Give me the sentences with this phrase inside. But in regex matcher, you don't know exactly what you want, but you know the pattern. Instead of, because otherwise you need to write all of them one by one. Assume that you want to extract dates or emails. Okay, you want to extract all the emails from clinical notes, clinical visits. So how do you do that? In text matcher, you cannot do that because you need to write all the dates here, which is impossible. Instead of doing that, all the dates have a pattern, like starting with digits and the slash, etc., or dots. Okay, four digits, etc. in regex. You can define that regex and then run it. You can just write one single rule and then get all the dates from your text, like thousands of text files.
Okay. So are you recommending using regex or the text?
If you know the pattern that you look for, like emails, phone numbers, test results. For example, measurements are can be extracted by regex. We do that for regex. We do that for example, blood count is 100 cc. So we have or Advil 1 milligram. So we know that pattern. We say that, okay, it starts with digit, there's a space, and then M or L. Okay, so we know the pattern. We can just build some regex pattern, like a complex pattern, and then extract them. Otherwise, I need to write assume that I want to get the dosages from text matcher. What would I do? I would do mg, lm, g, kg, etc. Right? I would need to write all of them. Okay. So for the finisher, you see that I ending up with some struct type again. To access, I use result and begin dot. Okay. But if you want to use, if you want to like get a clean version of your data frame so that you can save as a CSV file, instead of trying to do some exploding as I do here, or doing some PySpark manipulation, if you are not feeling very well on Spark itself, you can just use finisher. Finisher is removing all the previous steps, because if you want to end up with a clean version of your text by applying normalizer, tokenizer, stammer, lemmatizer, and you just want to deal with the clean version of the sentence, right? So you don't need the previous steps. So you can just use finisher, and you can say that I just want to deal with this column. So it will just give you the text column, the input column, like the first column, and then the desired column that you want, like a result column coming from regex matches. Because we usually worry about the result column, right? So I can just add finisher here, and I ended up with the finished regex matches. You see, so I can save this as a CSV file. I can save this, convert this to the pandas. Because if you don't do this, you cannot convert to pandas. Otherwise, there is no struct type, like a nested column structure in pandas. So we use finisher, or you need to write some functions, as I do with here. You see, I write some functions here, like a, okay. So now my schema is very simple right now. I have two columns, text and regex. So if I want to filter out the empty matches, I end up with this table, you see. So I just say that, okay, fine, finish regex matches is already there. I'm using the Spark function size. If it's bigger than, like greater than 1, use that, otherwise drop it. So that's what I get, which is very useful for your use case, I think. And the light pipeline. Right now we have been using stuff one by one. We were building the long pipelines, right, to do whatever we want. So assume that you want to have the same pipeline, but you don't want to apply this on a large data frame. You just want to do some tests. Or you have a model and then you want to get predictions from the user. You deployed, the user just enters something into the input box, and you want to return a clean version of that text, or find like a found matches out of that text. Okay, clinical entities, for example. How do you do that? Instead of trying to use all that Spark data frame, you can just convert into light pipeline. It will become like a pre-trained pipeline. You remember from the previous hour, we have the pre-trained pipeline. It's using the light pipeline as well, which is very like around 20 times faster than regular Spark ML pipeline. So you have the model, which is already fitted here. Like this is the model fitted on empty data frame, which means that right now I can save this, I can use this, I can do anything what I want. So I convert it into Spark NLP light pipeline, and then I can annotate. You remember the annotate method? For example, I want to have a large pipeline doing all the steps. Now I want to get a prediction from one single text instead of because otherwise you would need to wait if you have 1,000 columns. But you want to do one single text. For small text, Spark may not be desirable, but if you use light pipeline, it removes the overhead of Spark itself. Let's do this. Now I end up with a dictionary. You see, you remember from the previous lesson. So it says that there's no token because in the pipeline model we didn't use tokenizer, you see, which means that I will just, I don't need to do this. I don't need this comment actually because it's useless anymore. I can just write okay. There is no match here because there is no pattern like renal and cardiac is not here right now, you see. But if I run cleaning here, let's find a large to do some cleaning. Okay, let's do tokenizer and stemming and lematizer. Let's use this one. Copy paste pipeline model. It's fitted right now. Now I'm going to use it inside light pipeline. Same here, so I'll just use this. And let's see the keys. You see document, token, and stem and lemma is there. Now I wanna see lemma. Okay, the lemma version. Now I wanna see all. You see all here. Lemma and stem version of all of them. So if I want to do full annotate, I think you remembered full annotate. And then if I have a list of text, same. So you can do anything you want with the pre-trained pipeline and light pipelines, even though you create your pipeline because you were downloading that pre-trained pipeline to your disk from S3. But right now you build your own pipeline. Now you can convert it into the light pipeline and then get predictions as easy as this one, which is very Pythonic. Okay, we are done with the first section. Now we will start the second section, but we will have a break for 10 minutes. I need to drink some water. So if you have any questions, please feel free to ask. Okay, or have a break. Let's have a 10 minutes break. Okay, guys.
Back at 11:18.
Yes, like 15 or 18 as you wish. Or if you have questions, I will be here in 5 minutes. I'll have 5 minutes break, and then if you have questions, we can use that period as a questions as well. Okay. Or you can do some local tests on your local. Okay, we will start with words and sentence embeddings in the after 10 minutes. Okay, guys, I'm here. If you want to ask any question, you can ask for that as well. Guys, for the third notebook here, as you see, there is no slash between GitHub and Johnson All Labs, but there should be. So while you try to copy paste, please pay attention to that. I think there's a typo over there.
What's the token you changed in the light model pipeline? Light pipeline.
Come again?
Well, there was this token issue, token error, right? Which token did you insert?
Okay. Just before light pipeline, we have been talking about regex matches, right? And in regex matches, we have just two annotator in the pipeline, regex matcher and document assembler, which means that let's go back to, okay, document assembler and regex matcher. If I get a pipeline model from this pipeline, there will be three columns, right? Text itself, document, and regex matcher column, regex matches column, right? So if I try to get token column, there is no token column because I didn't put tokenizer here. So that's why I got tokenizer error, because the pipeline module has no tokenizer inside. So I got go back, run the previous pipeline here. In the previous pipeline, I have all of them, so that I could be able to reach token column.
Oh, okay.
Okay. We can close all. So this will be our new one. Now let's start with the slides. If everyone is here, I can start. And I'm telling again, on the third, you see here on the, in the chat menu, you see the third notebook. There is a typo over there between GitHub and Johnson All Labs. There should be slash on the link. So please manually fix that when you copy paste here. I just copy pasted and then added that this slash. Okay. Okay, I'm starting. Everyone's here? Guys, do you want me to wait or can I start?
I think you can start.
Okay, I'm starting. So, in this section, we will start from word embeddings concept, and I will just cover word embeddings, and then we will use pre-trained models, not the pipelines, but the models. For example, instead of using lematizer and defining our lookup table, we will use pre-trained models. We will use pre-trained named entity recognition models, pre-trained word embeddings. So we will do them as we do with pre-trained pipelines. So it is if you start using Spark NLP, it will be your daily job, like using pre-trained models again and again. For some of you who have no idea about the word embeddings and the word representation, in Spark NLP, in deep learning based natural language processing systems, we usually encode words and sentences. Not usually, we always encode words and sentences because we need some numerical representation in high dimensional space. Okay, so that's why we create some word embeddings, and there are some well-known word embeddings architectures like a Glow, like a FastAI, like Flare, etc. Right now I'm going to talk about the Glow word embeddings. So that we can get a specified dimension of word vectors for each token, so that we can find the distances, like using that dimensional distance, we can find the similarity between sentences. So the fundamental intuition says that words that occur in the same context, that is the whole reason behind word embeddings, by the way. The words that occur in the same context tend to have similar meanings. So if you train a word embeddings for your clinical text, you will have the representation of your clinical text. And then you can find the missing words like the sentence similarity or text classification by using our own word embeddings. In word embeddings, we usually have like specified dimensions. We will in Spark NLP we have 100 dimension, 300 dimension, 200 dimensions for different embeddings. So each word is converted to this vector. So this is just one single word, okay? Or sometimes we get the average of the vectors and we get a document vector as well. In Spark NLP, we have 4 different embeddings. For Glow, this is the mostly used one, and the first word embeddings available. We have 3 versions over there, like 100, 200, and 300 dimensions. We have Elmo embeddings. Like Elmo and Bird are the latest cool kids in NLP town. So they are hitting many benchmarks right now. So they are very successful doing some NLP tasks. So we also cover them, which means that we also have a pre-trained Elmo and Bird embeddings inside Spark NLP. And we also have Spark like universal sentence encoders, which is instead of trying to get the average vector of a sentence, because when every word has a vector, but when we get the sentence embeddings for sentence classification purposes, we get the average of the words. So it's sometimes for the long sentences or text, assume that you have one large paragraph. So when you get an average, you lose some meaning because it will be all flattened or the generalized. So instead of doing that, there's a cool encoder which we call universal sentence encoders, which is TensorFlow based. We also support that as well. And what's the main difference between Elmo and Bird and versus Glow, the old-fashioned word embeddings? In Glow, they are not context aware. So as you can see from this example, like the meaning of a word depends on the context it's in. Okay, so if you are using, like, I want to book an hotel, or I want to buy a book, in glow embeddings, book has the same word embeddings in each sentence, but in bird, they have different embeddings because their context is different. Okay, that's why we use sentences to define bird embeddings as well. Okay, so let's start coding again. We are going to work on third notebook. Please let me know if you are already here and seeing this Colab notebook and connected to the server. Okay, so I think you are all set, so we can start. And if you have a problem, you can just fix this slash issue here while copy pasting. Okay. Okay, I hope you already have. So I am starting to talk about Spark NLP pre-trained models. These are the pre-trained models that we have in Spark NLP. Like Lematizer, it's already trained on another TXT file lookup table, so you can just download it with this name. Like part of speech, you can use this way. So you don't need to train with your own text files or data set because we already have some pre-trained models. We have a clinical model list as well, which I will cover tomorrow, which means that you can have you can download pre-trained clinical models as well tomorrow. So these are NER models. We have different versions, like 100 dimension, 300 dimension, with different data sets, onto data sets, different word embeddings, etc. Let's start using them. So we will set up the Colab at first for Spark NLP. While it's loading, let me talk a little bit more about other words, other models. So we have the spell checkers as well. So you can just load that spell checker by using, by the way, the loading is not like pre-trained.load. It will be like symmetric delete model dot pre-trained in the parentheses this way. So you will see the notation right now. For example, NERDL, which means that name identity recognition deep learning model, is trained, needs some word embeddings, which means that I am going to use the word embeddings and this one in the same pipeline so that it will fit NERDL. Okay, so it's ready, I think here. Okay, ready. Let's start the Spark session. Okay, Lematizer. So let's download News category dataset. That is one of the benchmark datasets in text classification problems. Okay, I just downloaded it. It's here, News category test set. So let's read this into Spark data frame because this is the dataset that I'm going to use from now on. Okay, we have two columns, category columns and text column. This is the news data set. We have the news abstracts and category of the news. So the goal is to be able to find the classification, like find the topic of this text. This is the meaning of this text, this data set. So I'm going to use this one. So let's use Lematizer. You remember that previously I was using this way, the Lematizer this way, because I need to define, I need to give it a lookup table, but you don't need to do it right now because we have a pre-trained for English language. We support 5 different languages, by the way: English, Italian, German, French, Russia. Okay, so we have the, so how do we download it? How do we load it? You remember the name column from Spark NLP models. So we have a, by the way, let me show you that GitHub repo. Spark NLP models page. So GitHub page is public as well. So you will see all the recent models with the download link, so you can download from local. For the license, there's a license version. You don't have the download link here because it's licensed. So we will cover that tomorrow. Let's go back to here. So lemma, English lemmatizer's names is lemma and BNC. So we load it from just by giving the name, and it will download. It's around 1 megabyte. So it's pre-trained, which means that from now on, I don't need to define anything because it's already inside Lemmatizer right now. So as I told you before, I have the cache pre-trained folder under root. It's on your local folder, by the way. You see lemma is here because it's downloaded right now. So use it inside. So let's start with document assembler, tokenizer, stammer, and then Lemmatizer. We don't have any pre-trained model for stammer because stammer is rule-based. So there is no source like reference. There is no training for stammer. There is no lookup table for stammer. There is, but it's already like a rule. For each language there are some rules to apply some stemming. By recursively they are checking each chart again. Anyway, it's out of scope right now. So for the Lemmatizer, we need a lookup table, and it's already loaded right now. So we append Lemmatizer inside our pipeline and then fit. Okay, now on the news data set, I can apply this transformation. I can apply these steps, which means that I will get token count because I already had category and text. I told the pipeline that I'm going to use text column and give me the other columns like token, stem, and lemma. So it's already there. So we can just see the end result, as you may remember from the previous lesson. So this is the first token, like tokens from the first row and the lemma. Okay, lemma result. So let's do the same for part of speech. So we haven't used part of speech so far. We were just getting it from pre-trained pipelines. Let's download part of speech pre-trained model for English, which means that it will give me the part of speech tags of each token, like verb, adjective, adverb, etc. So let's download it. It's just 4 megabytes, and it will be here as well, downloaded. Let's use it inside our pipeline. So after Lemmatizer, assume that I want to use part of speech. Okay, I got the part of speech column here. Now I can see token versus part of speech, like each token corresponds to each part of speech here. Okay, let's have a nice view in pandas data frame. Now I am going to explode by getting the result of each attribute like token, begin, end, stem, etc. so that I will end up with this table. When you run this, you will end up with this table. Okay. Okay. You see, so right now I have the pandas data frame. I can use this anywhere I want in others for other Python scripts. So we can convert this to light pipeline as I showed a minute ago. So I have one text here and I want to apply all this pipeline with light pipeline. So I will just use light pipeline after fitting. This is what I get after fitting, and then I put it into the light pipeline. Then I have light model, which is very fast and useful for short data, like a small data sets. So I have the same here. Let's do some chunker. Chunker, I think you remember from the pre-trained pipeline lesson. We have some pattern, like start with DT and then adjective and then noun. Okay, so we can have the same. This is what has been used in that pipeline on the backend that we were not aware of. We were just downloading the match pattern model, like pipeline. Right now, this is what it is. So, which means that like give me the proper noun, or common noun, between common noun and adjective, and then starting with determinator. It's optional. So I built this pattern with part of speech, like without writing regex, right? So I just got a part of speech in the pattern, like regex. So I can use this inside after part of speech. Why part of speech? Because it needs to know this part of speech text. So I am pointing to this one, then saying that use document and part of speech column. Okay, chunker will use both input and then give me one output. So it will just get the post and then metadata and then map with documents. Okay, and then I get this one. Now I can transform it. I get the chunks right now. You see, let's see the chunks. So let's see the chunks and starting and ending indices of all the chunks detected. You see, these are the chunks that fits into the pattern that I just defined with part of speech. Like name, proper nouns, determinator versus like the, a. So these are the patterns that is found for top 10 rows, the first 10 rows, okay? So let's get to dependency parser. For dependency parser, we use part of speech column and token column and document column. These are all written in the document, so you don't need to memorize them. You just check and you get used to all these inputs whenever you use, because you usually copy paste. You will usually copy paste from your previous codes. So when you learn the basics, you will just see, okay, when I want to get a dependency parser, what column should I use in input? So you will just check your previous code and then get these lists. Okay, so I will use 3 input and then 1 output I will get. We have another dependency parser which we call it typed. The difference between dependency parser and type dependency, this gives the dependent token for each token. Like, let me show here. When we run this, we get this one. Okay, so dependency means that there is a relationship between representing and workers, and the dependency type is this one. You can find this dependency type by googling. What does it say? Universal terms. Word tree bank defines that. So Turner has a relationship with workers token, and the relationship is flat, etc. So at the end, you get this kind of relationship for your text. Assume that you wanna. So how do we use this? If I want to find, like, if I want to link the date entities, all the dates to the clinical entities. For example, he has a flu yesterday. He had a flu yesterday, or he's diagnosed cancer last month. Okay, so which means that last month should be linked to diagnosed entity. So this is how we do that in NLP. Spell checker. We can just load spell check Norvig. We have 3 different spell checkers in Spark NLP. You can just load this. This is already trained. Norvig Civitic model. And then when you run this, the steps are same, so I'm just skipping. When you do this, as you see, it's just using the token, because all I need to use is token column to fix that token, like spell checking. So let's see if there's a typo. Since there is no typo here, there is nothing to fix. But we can convert this to live pipeline to show you how, if it works or not. Why am I doing this? Because it was Spark data frame before. Right now, I want to test my pipeline with some small data, right? Just I want to give some text, and I want to get an output from that pipeline. And I have some typo here. I have 2 typos, patient and headache. So I'm assuming that my pipeline will fix this. But let's run the pipeline. Okay, now I put it into the light pipeline. You see, patient is fixed as patient, and headache is fixed as headache. You see, there was some patient, and in terms of NLP, if you use patient and patient, like these two are totally two different encoding. If you want to convert, like get some encoding for these tokens in NLP, if they are not same, you will end up with different attributes, but they are same. So you need spell checking to be able to make sure that you use everything we have. So word embeddings, we just talk about word embeddings. Let's see how we can use that in Spark NLP. We can just load glow 100 dimension word embeddings, which means that every token will get 100 dimension word embeddings, like a scalar value. So that it will be a matrix, like an array, so that I can use that as a feature for any Spark NLP purposes. So I just need token and document column as an input. This is loaded from S3. Let's load it. It will be 145 megabyte. So it will take a little bit time. And then I'm going to use it, for example, after tokenizer, which means that I want to get word embeddings of each token. It's downloaded, by the way. Now let's, by the way, I want to remind again, this is the first time that I do this. When you want to load from local disk, you can just use, instead of like pre-trained, you can just write load and then point to your cache pre-trained. Okay, so which means that you don't need to check S3 again and again, because whenever you run pre-trained, it will check S3 at first if this is updated or not. If it's updated, the updated version will be downloaded to your disk. If not, the one that is in your local will be used. So that's why you need to, you can use local if you want, which I usually do for my own work. And if you are dealing with sensitive data, PHI data, you usually work with an environment has no internet connection, maybe. You can just download all these models and then copy paste your cache pre-trained folder to your server, which is air gap network, for example, and then you will be able to load it from your local again and again. So let's build a small pipeline like a tokenizer and get the word embeddings and process it with the top 10 rows, and let's see the word embeddings. So this is the embeddings of, let's see the first token. Like unions. The unions word representation is this, like a 100 dimension list. Okay, so which means that I can just get an average of each word embeddings of each token, and then I will get a sentence vector or document vector. Okay, so let's see in tabular way. Okay, tokens and word embeddings. So I just exploded. So let's do the same for Elmo. To save some time, the steps are same, just how you see the numbers are different, because this is what the numbers that we get through Glow. In Elmo, we get another vector. Okay, so the same approach, just different model, because it's trained on different, trained with different architecture on different data set. It will get a different word vector. So with the BERT embeddings, which is the most famous one at the moment right now, like the most successful one, so it gets bigger, and now if we use this, we get another word vector for each word, but it's context away right now. In Glow embeddings, you always get the same word embeddings with this token. You always will. However you use this word, it doesn't matter. You always end up with the same word there for the same, because it's just lookup table for word embeddings in Glow. But in BERT, it's context aware. That's why we also use document or sentence column in word embeddings because it needs to know its position, or it needs to see the entire sentence to be able to define that vector. Okay, universal sentence encoder, you don't give any word, any token here, which is very good, by the way. If you don't want to deal with any text cleaning, if you see that your text is good enough and you don't want to do any text processing, you just want to classify, you can just convert your text into text embedding. Like assume that you have a sentence or document. When you do this, you will get a one single word embeddings, like a one vector for each document. You will get a document vector. So you see, which means that you don't. Before we used to see token by vector, but like we used to see vectors by token, but right now it's document. Like we have vectors for document, so you can just fit this to any random forest or logistic equation, and then you will end up with some text classification model. So if you want to load the models from local, you can just, this is our cache pre-trained folder. This is what is already downloaded. So you can use the same path and load it. Assume that I want to load from my local. This is my local path, and I just word embeddings model dot load, and then it will give up. It will end up with like give us glow embeddings column. And one important thing, if you are using Jensen, for example, and if you train your own word embeddings, you think that you have some specific data set which is very unique, which is very different from everything on public. You can train your own word embeddings, and then you can import it into Spark NLP in this way. So set storage path, which means that you use your own word embeddings, binary word embeddings. So it will be used in Spark NLP. So which is very cool. It will be available in Spark. Otherwise, you have no choice to use it in distributed environment. So let's get the sentence embeddings from each of them. I was mentioning that you get the average of each vector, of each token, to get a sentence representation, right? So we have sentence embeddings annotator in Spark NLP. It's like a lematizer or stammer. It's another annotator that we use. Its goal, its purpose is to get an average or sum of all the vectors representing a token, so that we can get a sentence embeddings. So we build a pipeline, document assembler, tokenizer, glow embeddings. So what I do, I put my text, I tokenize, get embeddings for each token, and then I get the word embeddings. Like the sentence embeddings, I get the sentence embeddings for out of all token embeddings. Okay, so when I do this, as you see, this is my average vector. Instead of token, right now I have sentence embeddings. It looks like universal sentence embeddings, right? Because in universal sentence embeddings, we had the sentence embeddings by itself, no need for tokenization, but right now we tokenize, so we got the average to the glow, bird, Elmo, which is very useful. So if I want to, which is very useful right now, if you want to find the similarity between two sentences, assume that you want to find a similarity between two sentences. Like I can use the sentence embeddings from the first row and the sentence embeddings from the second row, and I can just use this SciSpy spatial model, and then I can just calculate the cosine distance. This is what I get. So how can you verify this? If I want to find the similarity between first sentence and first sentence, like if I want to find the cosine similarity between two sentences, like same sentence, I can just say that, okay, give me the similarity between two same, right? Vector 1 is this one, vector 2 is this one, which is same. So if I want this one, I get 1.0, which means that they are identical. So it works. I just calculated the sentence embeddings and find the cosine distance. So if we have 100 sentences, so how we do that? For example, sometimes if I want to duplicate some clinical notes, there are some in clinical notes. I think you are aware that there are some copy forwarding all over the documents. The doctors are just copy pasting some text again and again. And when we want to build some model, we see some repetitive words, repetitive sentences which are useless, which are stayed or like left over there from someone else, which has no meaning. So to be able to remove some duplicates, what I do usually, I remove the stop words to find the duplicates, clean stop words, systemize, and then I will get like lematize, and then I get the sentence embedding and try to find the sentence similarity. And then if they are identical or more than 99, for example, 0.99, they are duplicate, I say that. So they have no meaning. So I can just drop one. So this is a one trick you can also apply. So for NERDL, we have 5 different NERDL models, pre-trained NERDL, maybe more than that. It every we change it. So NERDL, I think you remember its name with entity recognition. So let me see, where are we right now? Okay, it's about done. So this is the first NER that we have, which is public and free. So it gives you 4 different labels: person, location, organization, and others. Okay, so let's load it. It's just 14 megabytes. So which means that I can get these entities from my text without doing anything else, because it's already trained. So I can just, but what does it need? You see here. It needs token and embeddings because it's trained with NERDL architecture, which I'm going to cover in 15 minutes. NERDL architecture, we train our models with tokens and embeddings. So I need to put tokenizer and word embeddings annotator inside the same pipeline before NERDL. Okay. So I use tokenizer, word embeddings. Since I already know that this is trained with 100 dimension, when you are not sure, you can just check the source file. You will see that it's 100. And NERDL model is trained with 100, so we use the same embeddings in the pipeline. And then I added the public NER that is downloaded. So when I run this, what it will do, it will tokenize, get the word embeddings, and then feed into the NERDL model. And the NERDL model is already trained with these, so I don't need to get an average or anything. So it will just give out the label, like predict the label. So let's run this right now. It's not down, it's trying to download, but since it's already updated and in my local, it's just finished, right? Okay, it says. So let's see the labels that is detected or predicted by NERDL model. Okay, it's running, which means that when I run this, for the first row of news data set, it tokenizes, it gets the word embeddings for all of the tokens over there, and then gives out the NER label, which is very fast right now. All these calculations are done inside our pipeline, and then we have these predictions right now. Like this, which means that Turn Renewal is an organization. This is the first token, this is the second token, it says. Toronto is a location. So this is how it works in public NER. So we have Onto NER, which is very rich and it's also free. It has around 20 different labels, like cardinal, like first, second, etc. Date, event, factuals, like location, companies, language, everything. Like it's very useful. For example, if you want to extract dates from clinical notes, this is what you need to use. And you remember I was talking about date matcher, like getting the exact date from yesterday or next week. If you use that one after NERDL on top, you can at first extract the date Like yesterday is the date, it will be extracted so that you would sure that it will be cached, and then you can apply date matcher on date entities, which means that you will get some date for each entity is detected over there, which is very useful. We use that in real projects as well in this approach. So let's download onto a 100-dimension version of NERDL, and it's just 13 megabytes. So we download it, which means that it will tokenize the text, get the word embeddings, and then get the entities. So let's run it. You see, we get something cool here. Like Toronto is a location. GP means geopolitical entity. It's the abbreviation of location. Toronto organization, cardinal, like numbers are cardinal, means work of art, etc. So, as you see, we get token by token, like now. What if I want to get Federal Mogul as a one single chunk, or Turner Newell as a one single chunk, which we call it entity. So which we need to concat them by using that B and I. So we have another annotator for that, which we call NER converter. NER converter just use that label suffixes and indices, so that it would create a chunk for that list. Okay, so we tokenize. Sorry. We tokenize, get the word embeddings, get the NER labels, and then apply NER converter, which will give me meaningful chunks. So when I run this and then explode, you see what I get? So I got rid of all the B and I parts, and then I got the entire chunks. Okay, Southern California is a location. Mike Fitzpatrick is a person, etc. Okay, 70% is a person, because 70 is the first part, person is the second part. So if you don't want to do this on a data frame, you can do the same for light pipeline. You see, I just put into a text, and then I got this one as an output. I just collect. I use full annotate. Why do I use full annotate here? Has anyone an idea? Instead of annotate, why do I use full annotate? Because if I use just annotate, it will give me NER chunk result, because full annotate just gives out the results, you know, results attribute. But I also need metadata, entity metadata, so I need to full annotate. And if you also need some indices, start and end indices, you also need to use full annotate as well for the metadata. Okay, we are done with this notebook. So according to our plan, right now we can start with how to train NER, how to train your own NER. We have 1 hour left right now. I suggest we can just switch to this NER, how to train it, and then we will end up with text classification. Okay. Any questions so far? I hope you guys also play with on your local right now with the same collab notebooks. Or you can do that during the day and then let us know how it goes. So if you don't have any question, I will start with NER in the last hour. So NER is named data recognition. I think we already know what NER means. We are trying to extract some useful, meaningful entities from our text and assign some label for each chunk. There are some NER benchmarks that we compete with right now. Right now, Spark NLP has the highest industry level accuracy, which is a peer-reviewed results. So for the 2003 CoNNL dataset, this is what we get on test set and validation set. And these are the other libraries. So we are blazingly fast because we train on clusters, or you can even train on CPU without using any GPU. You can even train BERT models without GPU, but it's always better if you have GPU for the BERT. And you get a high accuracy with a few lines of code and and less amount of data. Okay, so how it works? We at first annotate our data. For example, if you want to detect all the metastases from your text, all the brain entities, or if you want to detect all the lab results from your text, you can just annotate your data like this way. You can say the brain, CT, etc. You can just annotate it, and then you will have a CoNNL file, which we call this CoNNL format. This is the CoNNL format token, part of speech, and NER labels. So your annotators or labelers annotate this one by using they just check it. They just click on one word. We have a tool, by the way, in Spark NLP in Johnson Labs, which we call it annotation tool. It can be deployed on your platform. You can just right click and then assign a label for annotation. So how it works in Spark NLP? We have the annotated data through our annotators, or we have a public data sets which is annotated by researchers, and then we read it by CoNNL reader in Spark NLP, and then use any word embeddings that we want, because our NERDL architecture uses char, CNN, BLSTM architecture. This is one of the state-of-the-art algorithms in NER research. So what we do is we use embeddings, one of the embeddings that we want, and then run our NERDL approach annotator, which is another annotator that I'm going to show you how to use it. This is where the training happens. Okay, so you select one of them and then select any other word embeddings. So let's start coding. Oh, I forgot to run Colab on the backend. Let's click on this open link and paste here. Okay, I'm connecting to server. Okay, it's connected, as you see. So let's set up the Colab environment. As I said before, you don't need to do this on your Databricks because it's already there. You just start with this one. You don't even need to do this because the Spark session is already there. You will just start from here for your Databricks. Okay, it's getting ready. And then we start. For example, if you want to train your NER with GPU, you can start your session with this way. Like you can use GPU parameter here. Is it true? So you will have a GPU enabled training. Okay. So the Spark session is started. This is a one-time thing. Then we will start how to prepare our data. To prepare our data, I'm going to use two public data sets from 2003, like people, organization, and location data set, which our public NER is trained on. I'm going to download it from our repo. It's here. Let's see inside. This is how it looks inside that CoNNL file. We usually create these CoNNL files for our purposes, for our clients, for where we annotate. For example, if you annotate your own data, you will have this format. You need to have this format to train, which we call it CoNNL format. Every sentence is separated by blank line, and every document starts with this line. And then every token has part of speech tag and NER label that we assign. In Spark NLP, NER, we don't need this second and third. You can just put anything you want here because we don't use part of speech in our NER training. Okay, as a side note. So NER, so let's read this into CoNNL. We have a CoNNL reader in Spark NLP from Spark NLP.training. We read the dataset and train dataset, which is already in my local. What it does, that CoNNL, you see this is the input, token, blah, blah. So I want to have an understandable data frame for my NER-DL model, right? So which means that I need to be able to train, I need to have this data frame out of this CoNNL file. So how would I do that? Either was I would try to split by spaces and then create a data frame, blah, blah. Instead of doing that, I will just read with CoNNL reader, and then CoNNL reader will give me text column, document, sentence, token, part of speech, and label columns. So it will assemble all the tokens as in sentence. It will get all the tokens in the token columns, and it will put all the part of speech in here and then labeled in here. So which is very convenient for my training right now. So it's ready, which is that easy. So this is the schema. So let's, I think it's already ready into there. So I have 14K sentences. Because when I do this, I got sentence for each row. Like this is one sentence, you see. So let's see what's inside. If I want to get aggregated statistics for how many entities I have per class, okay, let's run this. Now this is the like tabular way of seeing token, part of speech, and NER. Let's see some. I'm just exploding, getting the count for each, okay, for each one, like a value counts in pandas, and then order by this count, okay. So which means that right now I have this in my train set. I have 7K B log, 6.6K B per. These are the number of classes that I have, okay, number of samples per class, per label. So I read 100 dimension because I now assume that we want to train this model with 100D glow embeddings. You can use BERT here, you can use Elmo here, you can choose anything you want. It just needs a word embeddings. It will not download because it's going to download because I started another session with this notebook. It will download. Now it's downloaded. Now this is where the magic happens, okay, which we call it NER-DL approach. Okay, NER-DL approach. We have three inputs. We give it a sentence, token, and embeddings column. How does it get it? Because sentence and tokens are already coming from CoNNL reader. It's already in my data set. Embeddings column will come from the pipeline that is passing through word embeddings model, right? So I will feed all of them into my NER-DL approach, which is going to train this data set. And it will write the predictions outputs into label column, another column. No, sorry. It will use label column as a target column. Okay. And then it will give the predictions in the output column. And I will train one epoch. Let's just skip the training maybe. I can just show you the results. It will train one epoch. Learning rate is like 0.001. This is dropout ratio. If you are familiar with deep learning architectures, there's a dropout to prevent the model from overfitting. So this is the batch size. Batch size means like how many sentences I'm going to fit at one epoch. Okay, like not one epoch, like at each time, at each pass. And I can get the training logs, and I can say that, okay, use the 20% as a validation split. Right now, as you may realize, I'm using the entire data set to train. But usually in sklearn, in pandas, in Python, we split the test set as well. So we can do the same here. Okay, let's do that. But at first, let's do without splitting the test set and tell the NERDL approach that use the 20% of my train set as a validation set while training. I will just run this one, and then I can just fit. It will take 5 minutes to train a model, which is very fast. If you have your own data set, I'm not going to train right now because it might take some time. We don't have time right now. So we can just, if you get an error, there's another notebook already in the repo. The error for incompatible TensorFlow graph, because it's using TensorFlow on the backend. If your own data set has different parameters, like different number of, like different length of sentences, maybe you have just 3 labels, 3 NER entities, or maybe you have 50 entities. So which means that you need to create that graph manually. We are going to automate that process later on, but for now, if you get an error, we cover most of the architectures, but sometimes for specific words, specific data sets, you may end up with some errors. But if you have this one, there is another notebook. It's just 3 lines. 3 lines of code. You just specify how many labels do you have, how many charts do you have. How do you know this error? You will see in the error. When you see that error, you will see how many charts you need. Okay. Okay, so when you train this, there will be a folder created on your local, on your home folder, which we call annotated logs. In annotated logs, you will see the training logs. In the training logs, you will see these parameters. I just cd into that folder and then read the logs. Okay, when I read the logs, I see that the first epoch is started, and this is my data set size, and the validation sample is this one, which means that like I have around 13K in total. This is the train, this is the validation, and this is the validation matrix. You see, after just one epoch, this is what I got as a F1 score. You see, with the last column, which is very good. And this is the graph file that I was talking about. It's already there, but when you get an error, you will need to create your own. We have 9 labels, 9 class, like when you count 1, 2, 3, 4, 5, 6, 7, 8, and other label. There is a O letter, which is the 9th label, which means other than this. We have 9 class. So if you want to test this on your test set, I can just read the test data set into CoNNL as well. And then I need to transform it with Cloud embeddings. Why do I do that? Because to be able to get a prediction, now I have a model trained, right? NERDL model is already trained. It's already there. The training is finished. I have a trained model right now, fitted model. There was no training before, but I was just fitting on an empty data set, you remember. Now I train the NER, the real NER model. So I have an NERDL model. Now I want to test this on an unseen data set. What do I need to test it? I need to know word embeddings and tokens, right? Sentence, word embeddings and tokens I need to know, which means that our CoNNL reader already produces token and sentences. So I also need word embeddings. So I use the same word embeddings to get word embeddings column. Now it's ready to get prediction. When I do this, I just transform on test set. So this is my fitted model. This is my test set, unseen test set. Now I want to get prediction. Assume that this is just prediction. Transform means prediction in Spark NLP transforms. Now, and then these are the predicted results. So after just one epoch, this is what I get. Okay, like cricket is O label. This is O label as well, just hyphen. This one is B organization. Okay, London is B location. You see, which means that I have the. But by the way, this is the ground truth, and these are the predictions. Why is that ground truth? Because I'm using the. Okay. Label is the ground truth. NER is the predicted output. You remember my pipeline, right? Let's go back to pipeline. For my pipeline, as you may remember, I have the token, part of speech, and label column. Label column was my labels assigned by annotators in the ground truth. And then I added embeddings column over there. And then I trained my model. The predictions will be in NER column. You see, the prediction will be outputted into NER column. So at the end, when I do this, I will have a NER result. So this is what I get. This is ground truth. This is ground truth. And this is the prediction. This is ground truth. This is prediction. So let's do the test evaluation, which means that as we do with a sklearn, you know, like we just get predictions and then use classification score or confusion matrix. Let's do the same here. To be able to do that, I need to explode, because this is struct type. I can explode as a ground truth and prediction column. Okay, I will just convert this one into explode, and I get this view, which is very familiar, right? Token, ground truth, and prediction. Now I can convert this to pandas. I just convert to pandas here. And then I use classification report from sklearn, which is very familiar for most of you, I think. And then I got the classification report. You see, this is the test matrix. The one I see in the annotator logs was validation matrix, because I'm not able to get the validation matrix when the training finished, right? I can just see the logs. I can just check it with the logs. If I want to test it with an unseen data set, this is the way that you do that. There's also another way that you define while training the test set. Like every epoch, you get the predictions from, like, metrics from the test set as well. But it's out of scope right now. But it's in the documentation if you want. Okay. I was talking about you can also split your train data set. Assume that we read train, like we read the train, and then now we want to split it. You can just split it. This is a random split function coming from PySpark, like Spark function. This is like Spark method. So it says that 30%, 70% split it randomly. Now I have two data sets, training data and test data, which means that I can use the training data for training, get some validation scores, like the 20% of the training data will also be used for validation. And then I can also test it on the test data after that, as I just showed you. So this is how you do this. You know, test, like get the embeddings from test data and then get the predictions from test data, which already has tokens and embeddings. So assume that you trained that, now you are ready. Now you want to deploy your model or use somewhere else. So how you do that? Since NERDL model is a pipeline itself, pipeline model. You remember that when I fit a pipeline, it's pipeline model. And the pipeline model has stages. Like word embeddings model is the first stage, NERDL model is the second stage. Why is that? You remember NERDL model? Yes, here. You see here, embeddings and NER tagger, like the one that makes the training. So I want to save this part. To be able to save the, but after fitted, which means that I'm going to save the fitted part of the pipeline, NER pipeline. So I will just check what is the stage of NERDL model. Okay, it's here. So I will just, because when it's fitted, it becomes NERDL model. Okay, NERDL approach becomes NERDL model when I fit it. So it's the stage 1 according to this list. So I can just write it to the disk as a this one. So which means that I can use this NER like I download public NER or onto NER. You remember I was just downloading onto 100 by just saying NERDL.pretrained in the parentheses NERDL or onto 100. So we can do the same here when you train your own model. So let's get a prediction pipeline. Assume that you have saved this pipeline. Now you want to get prediction on somewhere else. You deploy some API, people just feed their document and get some entity labels. So you can build a prediction pipeline, which is the same pipeline that we have been talking so far, like get the sentence, splitter, tokenize, get the word embeddings, load my NERDL model, right? So this could be onto as well. This could be public NER as well. So this is the one that we just trained. And then NER converter to get an exact chunk, you remember? And then we have a prediction pipeline right now. When you do this, you can fit on empty data because it's already fitted. So we just need a pipeline model to be fitted on empty pipeline. And now we are done. So I can just fit this text, convert the Spark data frame, and get a prediction. Just after one epoch, you see, after 5 minutes, I have a running model right now. You can do the same with the live pipeline. I think you're already familiar with these concepts. So I can just convert into live pipeline and then annotate my text. So which means that I can get this one, like per label per token. So I can also get token, start indices, end indices, and NER label by using full annotate, because full annotate will let me access the indices as well and the metadata. So we are done. The last part of NER, if you want to create your own CoinNL dataset, there's another, the same pipeline. You can just use some like for loops. I'm not going to get into the detail, but you will have the notebook, so you can do the same. For example, I just created a pipeline, sample pipeline. I told that get the predictions and assign as a the last column, and then write one by one with the spaces next to each other. You see, it's very easy. So which means that you have a CoinNL file. If you have an Excel file with the predictions, like with the annotations for your own use case, you can just write your own for loops or function to create your CoinNL files, and then rest would be handled in Spark NLP. Okay, we are done with NERDL. We are going to spend the last 40 minutes or 30 minutes for text classification. Any question? Okay, now we are ready. This is the last part, which we call text classification with classifier DL approach that we just added a few months ago to Spark NLP. So we have our own TensorFlow architecture running on the background. So you just feed your text with the embeddings that you select from Spark NLP. And then our classifier DL will build a model just like we did with NERDL, okay? Which is very fast, which is very easy to use, requires no deep knowledge. You don't need to get inside the architecture as well. We just try to come up with the best architecture for you in Spark NLP. It works up to 50 classes, and you can even use 1024 dimension word embedings. You see all the possibilities here. So you don't need to define, because in Spark ML, not Spark NLP, in Spark ML, when you try to build some text classifier, it's a long process. Even in TensorFlow, it's a very like more than 1,000 rows lines, of course, you need to write to prepare your text. Okay, even in Spark ML. But in Spark NLP, when you have just a text file, you can just follow all the steps that I prepared so far. Like you will just read that text into data frame, use any word embeddings that you want, and get a word embeddings, and then feed into classifier deal. That's all. We use on the backend, we use this architecture, which is very scary right now, but you don't need to deal with it. It is going to be handled. And let's code. Let's see how it works. It's very fast and easy, and this will be the quickest part, I think. Text classification is the major problem, major use case for any NLP problem out there. So right now I start the session. So if you want to, for example, NIFS category, I wanted to load NIFS category to train and test set. So I downloaded them. So I have two data sets, train data set and test data set. I'm going to train my classifier on train data set and get a prediction on test data set. Okay, so they're all downloaded right now. Let's see what's downloaded. These two files are downloaded. So I have the train data set. Let's read into the Spark data frame. Now it's loaded. How many rows do I have in total? 120,000 rows that I have. Let's see the distribution of the categories. We have 4 categories here. The categories are from world category, it's 30K. Science fiction, like science technology, it's 30K. Sports, 30K. Business, 30K. Okay, it's an evenly distributed. So there is no imbalance problem right now. So which means that I want to predict the class of news on unseen data set. So let's read the test data set as well. So I get that call error, which means that it's a PySpark SQL function. Okay, which means that we have around 2K per class in the test set. This is unseen test set. So I'm going to train a model in train set and get a prediction on test set, which we usually do for any other problem that we have. So if you want to split your data set, you can also do the same that we did in NERDIA, which I suggest you should do that, so that you would know before testing your data on the real data set. Assume that you gathered some 1,000 rows, and you want to build a model with just small amount of data, which means that to make sure that it works well on unseen data set, it's a general principle that we split like 80% as a train, 20% as a test set. Okay, you can do the same so that you would know how well your model is doing on unseen test set. Okay, let's start classification. What we do, if I will show you 2 different methods in Spark NLP. One is a long way, and the second one is very short, very easy to do. The long way is there because if you want to do some text cleaning, text processing or normalization before building classifier, which is usually the case in real-world NLP problems, you can just build this pipeline, which I have been talking so far. Like you can feed into the document assembler, get the tokens, normalize, like remove all the digits and punctuations. This is what it does, you know. And remove the stop words and get the lemma right? Why do we get lemma? Because we want to get the most meaningful part of any token, so that we remove some unnecessary suffixes like plurals, like past verb version of each verb, etc. Okay, then we get the embeddings. So which means that I have one single text, I clean again and again, and then at the end I get the embeddings of the most clean version of each token. Then I get the sentence embedding by averaging, and then I feed into classifier DL approach. So if you think that this is long, you need to see how it is being done in sklearn. It's more than this one in sklearn, in any NLP problem. So even the longer version of how we do this in Spark NLP is shorter than how it is being done in other libraries. If you want to check spicy text classifier, you will see more than 500 lines of codes. Or transformers or Hugging Face, you will see thousands of lines of codes. But in Spark NLP, even the long version is shorter than all of them. So when we train this, let's build this pipeline. What's going to happen right now? It will be downloaded, like the lemma model. It's a pre-trained model, will be downloaded. And word embeddings pre-trained will be downloaded. The default one is downloaded. Default one is 100 dimension glow. Okay, it's done. So which means that I'm ready to train. So I'm going to, this is CLF pipeline that I call it. Now I'm going to fit train data set. Like I'm going to fit my model on train data set. I just did this for 10 epoch. Okay, I can set, let's talk about here. This is the classifier DL. This is the classifier DL approach that I'm talking about. This is where the magic happens for the classification. I just fit sentence embeddings because all it needs is a sentence embeddings. Classifier DL just needs some embeddings, like a list of numerical values in embeddings format. Okay, and then it will give the prediction in the class output. You can just name it like a prediction class, prediction column, and it will use the category column as a ground truth and train 3 epoch or 10 epoch or 50 epoch. So you can just check the output logs and then decide if it is learning well or not. Okay, yesterday I tried to train this for 10 epoch and it took, I just wanted to see how it works in Colab. It took 8 minutes. Colab has very decent, like below average configuration because it's free and provided for Google by Google for everyone. So it's not a good server, but on your local it will be like a take a few minutes maybe. So it took 8 minutes for 10 epoch, and as in ERDL approach, you will get the logs here. You see each epoch we get some accuracy metrics, which means that after 10 epoch we have 90% validation score. Okay, so as you see, the accuracy is increasing, which means that the model is learning. When you train longer, if you see that the model accuracy is getting like a, I think you already know the basics of deep learning training process. Like you check the loss and your accuracy, and then try to decide if it's overfitting or not. So I'm not going to cover that concepts here. So that you can decide how many epoch that you want to train, or maybe you want to play with your learning rate, or you want to train, you want to change your batch size. These are all important parameters that you need to play with: epoch, learning rate, batch size. Okay. And then when we get our model, you can get some, this is the prediction step. Now our model is ready, right? I can put it into the light pipeline as well, or I can just get a prediction on the test set. Let's see how it performs on unseen test set. Okay. So this is the ground truth category column. This is the text column, and this is the result column. My model predicts these labels after 10 epoch on unseen test set. You see there are some bad predictions here, which means that I can try to see what's going on, or I can increase the EPO, or play with the learning rates, or I can do some more text processing maybe. You see, looks good. Let's see. I can just convert this to pandas, like a format. So these are all, which means the classifier DL can predict label for each sentence. If this is a sentence that you give, like this is a text and has multiple sentences, which means that it can assign labels for each sentence, which is very unique feature, by the way, because we usually don't have any such kind of feature in another library, because when you give a text and you want to get a prediction, you need to split the text and then run your prediction model in a loop. Okay, but in Spark NLP, since it's all done in pipeline, you just give a whole bunch of text, and then it will be split into text and give out predictions for each sentence. Since this is an array, you can just apply some lambda function and then get rid of the array, and then just use the bare version, and then this is the test matrix. Just after 10 epoch, we have 90%. Okay, and this was the longer version of how we train. Longer version means that we do the text processing, text cleaning steps as we have been doing in NLTK or Spicy. So if you don't want to clean your text, you have just your text and you want to get predictions, and you don't want to deal with what's going on inside. We are using universal sentence embeddings for that. As you may remember, it prepares, it gives sentence embeddings for each text that we provide. So you don't need to deal with tokenization, averaging, sentence embeddings, etc. So if you are using the public dataset, it may not work well on clinical dataset, maybe we need to test it further. But since it's trained on a large Wiki and Google News dataset, which means that it's a large model trained by Google itself. So we are just going to use that pre-trained model, pre-trained embeddings. So what we do is, it's just 3 steps. Of course, we start with document assembler, and then universal sentence encoder. We just load it. We just point the document column as an input, and then sentence embeddings will be calculated, and then we will run classifier DL approach. Just 3 steps. So which means that just 10 lines of code, we have a classifier, like state-of-the-art classifier right now. We just gave it the text, raw text, ugly text as an input, and then classifier DL is try to predict the class. Okay. When we run this and then see the logs, we will see the similar logs. This is the second logs that you see, which means that I have another logs. Now I open that logs. Okay. And I see that it's even doing better. You see, like after 5 epoch, I have 90.3. Let's see the previous approach. After 5 epoch, I have 89.5. You see the difference, which means that without text cleaning, just by using one universal sentence embeddings, without cleaning my text, I get the same accuracy in half of the epoch. Okay, so which is very fast and easy to train. So after just 5 epoch, when I get the test metric accuracy, it's not here by the way, but okay, let's get prediction from the trained model. Since I didn't train right now, I'm not going to calculate the test metrics, but it's still valuable to compare the validation metrics. Okay, now I have the pipeline model. This is the pipeline model that I trained here. Use CLF pipeline model. Okay, after fitting, I have used pipeline model. Now I can use this. I can put into the light pipeline so that I can get fast inference, right? Fast prediction. Assume that you have some model that you deployed with Flask maybe, or Streamlit. You can just use light pipeline for small amount of predictions, because if you want to get predictions from 1,000 documents, you can just use pipeline as it is. But if you just want to test it every once in a while with small inputs, like short text, I strongly suggest you use light pipeline, as I have been suggesting so far. And now I fit this text. It's like recent COVID text, like fate of Italy. And then I want to annotate, and the prediction is business. Let's give that. Okay, and I can do the same. I can save this pipeline as well as I do with NERDL. Let's see the stages of my pipeline model. Where's my classifier DL? It's here. Classifier DL approach has become classifier DL model after fitted, right? So I can just check the 0, 1, 2, okay, stage 2, and then write as this one, and then I can load later on, and then I can build another prediction pipeline. Okay, now we covered everything. We have everything. When we go back to slides, you will see some resources here. Let me talk a little bit about these resources. We have Spark NLP official page, nlp.johnsnowlabs.com. Okay, you will see some samples, examples here, and we have official documents to let you start with. So you will see all the examples here as well. You can just play with it. But if you want to see the working solution, the public workshop that I just prepared for this training covers everything that you need. Because we also, let me show you something. When you go to workshop repo and tutorials, and certification trainings, you see right now we covered first, second, third, and fourth, and fifth. I put some other stuff here. You see this notebook 5.1. This shows every possible combination of text classification in Spark ML and Spark NLP, like TF-IDF, count vectorizer, Elmo, BERT, how to train your text classifier with BERT, how to use TF-IDF with random forest, how to use BERT embeddings with random forest. So it covers all the possible combination of text classification problems in Spark, which is it's very long notebook, so you can just check it if you want. I also put playground data frames, which means that how you can use some Spark functions like collect, size, show, how to filter, how to slice, etc. So which means that you may want to play with it. Then you could feel comfortable. And we have the YouTube channel, John Snow Labs YouTube channel. When you Google it, you will see that we have some few videos right now, but we will enrich that later on with these training videos. We have blog posts. We have blogs on our website. Let me show. You will see all the blog posts and the articles for different, like for data market, but we also have Medium articles, like Medium. Let me show that to you. You see, we already have these articles published over there, and towards data science or KDG Nuggets, or our own Medium channel. Okay, so the most popular one is NER with BERT, how to train your NER model with BERT. We just published a month ago. And we have a large article here, which is called Introduction to Spark NLP. This is the first article that you may want to read at first. This covers all the articles, like all the bits, every bits of Spark NLP, like everything that I try to cover most of the time during this training. It's very, so you may want to read what's approach, what is annotated, what's transformer. Okay, so we also have other articles that is written by our guys, our team members. and published on different websites. Okay, and these are the slides and collab links. Okay, I'm done. We can spend the last 10 minutes for questions and answers if you want. Has everyone tried to replicate the same while I explaining?
Most part of it.
Okay.
Yes.
Most of the concepts could be a little unfamiliar at the moment, but when you start playing with it, you will get used to that. The learning curve would be a little bit steep at the first few days, and then when you get familiar, you will not want to use any other NLP library, I think.
So this kernel file, how big is this one? And
Okay, let's get back to kernel file. Okay, it's 14K. So if you are asking that, how much data, custom data that you need to, if you want to annotate, right? Because it's usually the use case that we do for the clients during POCs. So let me give you some real world examples. Just 100 entities per label, like 100 samples per label would be enough for specific healthcare problems. That's what I see from other projects that I have worked so far. Like just by using 100 patients source file, text file, like clinical documents, we could be able to develop some reliable NER models over 80% F1 scores. Because we are going to use we use clinical word embeddings. I'm going to explain that tomorrow. We have clinical word embeddings like Glow or from PubMed, which means that we also have some power coming from pre-trained models.
got it.
So right now we see it like more than 7 or 6K per label. So in healthcare, I remember that we have some 100, just 100 or 60 or 50. And we could be able to build a nice model. Because this is domain specific. The one that we want to build is domain specific, which means that when we use your own data, it will be good to, it will be nice to see nice accuracies at the end, hopefully.
Yeah.
I have a question.
Okay.
Yeah. Hello.
Hello. Hello. I'm listening.
Yeah. It's the question is how we can use the pre-trained model for the healthcare. The glove you showed us is a kind of similar with the pre-trained original glove. Which one is a pre-trained word embedding for the healthcare?
The pre-trained for the healthcare is not here right now. I'm going to cover that tomorrow. But if you check our models, Spark NLP models page, you will see clinical version. Okay, so we have NER clinical, assertion, pathology model, etc. And we also have word embeddings, clinical word embeddings. You see here, and ICD word embeddings we have. We have 2 different word embeddings for the clinical purposes, which is trained on 2 different data sets.
Okay. Thank you.
Okay. You can just for the NER project to get used to get some proficiency how to use NER models. You can just Google some NER datasets and then try to convert into CoNNL file like this way. Like if you have some text, assume that you have text, and there are some people over there already annotated, Peter, Parker, etc. So if you have this kind of Excel file, you can just create a CoNNL file as you wish by using Spark NLP annotators. It could split the tokens and then assign some indices, and then you can keep track of to map it. Like Beeper is coming from your annotator, Peter is coming from your annotator. Okay, so which means that if you don't have the O labels, you can get all these tokens from your Spark NLP pipeline. If you already have the O in the annotations, which is very easy for you, you will just use 2 columns because we don't use the part of speech columns in NERDL, as I mentioned before. Our architecture ignores that. So you will just token and label that is coming from your annotators. And then when you have an Excel file like this, you can just loop through and then create a CoNNL file and then read with CoNNL reader and then train. It will take like less than 30 minutes if you have a labeled data set.
Yeah.
Okay, guys, I think we are done. We will meet together again tomorrow morning at your time.
Okay.
And then we will do some Spark. I hope that you play with these notebooks till tomorrow so that you could feel much comfortable, so that you would get much value for the tomorrow's meeting. In tomorrow's training, we will cover the Spark NLP clinical models and how to train you already saw how to train your model in your model, but I will show you how to use pre-trained clinical models, assertion and ICD-10 models, etc.
Okay.
I think it will be much more familiar for you. Okay.
Okay.
Thank you.
I thank you as well. Anything else?
How will you be sharing this recording?
Okay. I think it's still recording. After the session finished, I will see what I can do. I will also talk.
Okay.
I will also need to talk to David about this so that we will find a way to share it with you. Okay.
All right. Thank you.
Okay. I thank you as well.
All right.
Okay, guys. We can end the session.
Talk to you guys later. Bye-bye.
Okay. Have a nice day. Bye bye.
You too.
Mm.